In this video, you'll experience the most beautiful and fascinating theories the universe has to offer, from the Big Bang to cyclic universes. We'll dive into the poetic side of physics. Don't forget to subscribe and like if you enjoy this. Also, feel free to comment how late it is for you and where you're watching from. And now, I wish you a good night and hope you enjoy listening. The Big Bang Theory. Imagine holding the entire universe in the palm of your hand. Not the universe we know today, with its countless galaxies stretching across billions of light years, but the universe at its very beginning, compressed into a point smaller than the period at the end of this sentence. This is where our cosmic story begins, with perhaps the most profound idea in all of science, the Big Bang Theory. 13.8 billion years ago, everything that would ever exist was contained within a singularity of infinite density and temperature. Space itself didn't exist yet. Time had no meaning. The very concepts of before and after lose their relevance when we peer back to this moment of absolute beginning. It wasn't an explosion in space. It was the explosive birth of space itself, the moment when the fabric of reality first began to unfold. In that first unimaginably brief instant, the universe began expanding. Not expanding into something, because there was no something to expand into. The fabric of reality itself was being woven for the first time, creating the stage upon which all future cosmic drama would unfold. Temperature and density were beyond anything we can truly comprehend. Conditions so extreme that the fundamental forces we know today were unified into a single, primordial force that governed all interactions. Within the first fraction of a second, as expansion continued and temperatures began to drop, the universe underwent a series of phase transitions that shaped its fundamental character. Gravity peeled away first from the unified force, becoming the gentle giant that would eventually sculpt galaxies and guide the dance of planets around stars. The strong nuclear force separated next, destined to bind quarks into protons and neutrons, and hold atomic nuclei together against the electric repulsion of their charged particles. The electromagnetic and weak nuclear forces would separate slightly later, completing the quartet of forces that govern all interactions in our universe. These weren't gradual changes. They were phase transitions as dramatic as water suddenly becoming ice, but on a cosmic scale that defies imagination. Each transition fundamentally altered the nature of reality, determining which particles could exist and how they could interact. The universe was writing its own rulebook in those first moments, establishing the physical laws that would govern everything from the smallest quantum interactions to the largest cosmic structures. As the universe continued to expand and cool, the first particles began to form from the seething energy of creation. Quarks and antiquarks condensed from pure energy, immediately binding together under the influence of the strong force to create the first protons and neutrons. For the first time, matter as we understand it began to exist. But the universe was still far too hot and dense for atoms to form. Any electrons that tried to bind to nuclei were immediately knocked away by the intense radiation that filled all of space, creating a cosmic soup of free particles and photons. During these early moments, the universe underwent a process called Big Bang nucleosynthesis. The conditions were just right, hot enough for nuclear reactions, but cool enough for some nuclei to survive, allowing the first light elements to form. Protons fused with neutrons to create deuterium, which then combined to form helium nuclei. Small amounts of lithium also formed during this brief window of cosmic chemistry. This process lasted only about 20 minutes, but it determined the primordial abundance of light elements that we still observe throughout the universe today. For nearly 400,000 years after this brief period of nucleosynthesis, the universe remained opaque, a glowing fog of particles and radiation. Free electrons scattered photons continuously, preventing light from traveling far through space. The universe was like a dense, luminous cloud, glowing with the heat of creation, but impossible to see through. Temperature and density slowly decreased as expansion continued, but the cosmic fog persisted. Then came a moment cosmologists call recombination. Though it was actually the first time electrons and nuclei combined to form neutral atoms. The universe had finally cooled enough for electrons to join with nuclei, without being immediately knocked free by ambient radiation. Suddenly, light could travel freely through space for the first time. The cosmic fog lifted, and the universe became transparent, allowing photons to stream across vast distances unimpeded. This ancient light still surrounds us today, filling every cubic centimeter of space with faint radiation. We call it the cosmic microwave background radiation, the afterglow of creation itself, now stretched by billions of years of cosmic expansion from visible light into microwaves. When we detect this radiation with our satellites and telescopes, we're literally seeing the universe as it was when it first became transparent, looking back to within a few 100,000 years of the beginning. This cosmic baby picture shows us a universe that was remarkably smooth, with only tiny variations in temperature and density that would later grow into the galaxies and large-scale structures we see today. The Big Bang Theory explains so much of what we observe in our universe. It predicts the abundance of light elements like hydrogen and helium that we see throughout the cosmos, matching observations with remarkable precision. It explains why the universe is expanding uniformly in all directions, with distant galaxies receding from us at speeds proportional to their distance. It accounts for the temperature and characteristics of the cosmic microwave background radiation, including the tiny fluctuations that seeded the formation of cosmic structure. The theory also explains the overall architecture of the universe we inhabit. The initial conditions set during the Big Bang determine not just the types of particles and forces that would exist, but also the large-scale geometry of space itself. The balance between the kinetic energy of expansion and the gravitational attraction of matter determined whether the universe would be open, closed, or flat. And observations suggest we live in a remarkably flat universe, poised precisely between eternal expansion and eventual collapse. What makes this theory truly beautiful is its profound simplicity and explanatory power. From a single point of infinite possibility, all the complexity we see around us emerge through the action of fundamental physical laws. Every atom in your body, every star in the sky, every galaxy scattered across the cosmic web, all of it traces back to that first moment of creation. The carbon in our cells was forged in stellar cores. The oxygen we breathe was created in dying stars, but the hydrogen that makes up most of our bodies dates back to those first few minutes after the Big Bang. We are, quite literally, children of the Big Bang, made from elements created in the primordial furnace of the early universe and the stellar factories that followed. The theory connects the largest scales of space and time with the most intimate details of our existence, showing how the cosmic and the personal are inextricably linked through the grand narrative of cosmic evolution that began with that first moment of infinite possibility, 13.8 billion years ago. Cosmic inflation. In the tiniest fraction of a second after the Big Bang, a period so brief that it challenges our ability to even conceive of time intervals that small, something extraordinary happened that shaped the entire future of our universe. This is the realm of cosmic inflation, a theory that describes how the universe underwent a period of exponential expansion, faster than the speed of light itself, transforming a region smaller than a subatomic particle into something larger than a grapefruit in an instant that defies human comprehension. We're talking about the first 10 to the power of minus 32 seconds of cosmic time, a duration so impossibly brief that it makes a blink of an eye seem like an eternity. To put this in perspective, this interval is to 1 second what 1 second is to about 10 trillion times the age of the universe. In this incomprehensibly brief moment, a region smaller than a proton expanded by a factor of at least 10 to the power of 26, growing from quantum mechanical scales to macroscopic dimensions in less time than it takes light to cross the diameter of a proton. This might seem to violate Einstein's rule that nothing can travel faster than light, but inflation doesn't involve anything moving through space. Instead, space itself was expanding at an exponential rate. Imagine dots drawn on a balloon that's being inflated at an ever-accelerating pace. The dots aren't moving across the balloon's surface, but the surface itself is stretching, carrying the dots apart. During cosmic inflation, this stretching happened at a rate that makes the fastest balloon inflation seem glacially slow. The driving force behind inflation was a quantum field called the inflaton field, a form of energy that permeated all of space with enormous energy density. Unlike matter or radiation, which become diluted as space expands, this field had a peculiar property. As space expanded, instead of becoming less dense, the energy density remained essentially constant. This created a kind of cosmic feedback loop. The more space expanded, the more energy was available to drive further expansion, leading to the exponential growth that characterizes inflation. During this period of rapid expansion, the inflaton field existed in what physicists call a false vacuum state, a temporarily stable configuration with enormous energy density. Think of a ball balanced precariously on top of a hill. It's stable for the moment, but any small disturbance will send it rolling down to a lower energy state. The inflaton field was like that ball, poised in a high-energy state that couldn't last forever, but could persist long enough to drive cosmic inflation. The quantum nature of this field means it was subject to quantum fluctuations, tiny, random variations in energy density that are an unavoidable consequence of Heisenberg's uncertainty principle. Under normal circumstances, these fluctuations would be microscopic and short-lived, but inflation did something remarkable. It stretched these quantum-scale variations across vast distances, preserving them as macroscopic variations in the energy density of space itself. These quantum fluctuations became the seeds for all the large-scale structure we see in the universe today. Regions where the inflaton field had slightly higher energy density became the locations where matter would later clump together under gravity's influence, eventually forming the cosmic web of galaxies and galaxy clusters that stretches across space. In essence, the quantum mechanical uncertainty principle, operating at the smallest possible scales, left its fingerprint on the largest structures in the cosmos. Inflation elegantly solved several puzzles that had long troubled cosmologists. The horizon problem questioned why distant regions of the universe that could never have been in causal contact, regions so far apart that light hasn't had time to travel between them since the Big Bang, nonetheless have almost exactly the same temperature and properties. Without inflation, there would be no way for these regions to have reached thermal equilibrium. Inflation resolves this puzzle by showing that these apparently disconnected regions were once close together, in intimate contact, before being stretched apart by the exponential expansion. They had time to reach thermal equilibrium before inflation separated them beyond any possibility of communication. The universe we observe today, stretching for billions of light years in every direction, all originated from a tiny region that was once small enough for all its parts to be in thermal contact. The flatness problem wondered why the geometry of space appears to be almost perfectly flat, balanced precisely between the positive curvature of a closed universe and the negative curvature of an open universe. In most models of the Big Bang, the universe would need to start with incredibly fine-tuned initial conditions to remain flat for billions of years. Any significant initial curvature would grow over time, leading to a universe that quickly becomes obviously curved. Inflation solves this problem through pure geometry. Any initial curvature would have been stretched out by the exponential expansion, just as the surface of a balloon appears flat when you're standing on it, even though the balloon itself is curved. After inflation expanded space by such an enormous factor, any region we could observe would appear flat, regardless of the overall geometry of the universe. Inflation naturally produces the flat universe we observe without requiring special initial conditions. Perhaps most remarkably, inflation makes specific testable predictions about the cosmic microwave background radiation, the afterglow of the Big Bang that we can observe today. The theory predicts that primordial gravitational waves generated during inflation should have left distinctive patterns in this ancient light, patterns called B-mode polarizations that would be the smoking gun evidence of the inflationary epoch. These gravitational waves would be fossils from the inflationary period, ripples in space-time itself that have been stretching across the universe for nearly 14 billion years. Detecting them would be like finding the signature of inflation written in the very fabric of space and time. Several experiments are currently searching for these subtle signals, hoping to glimpse direct evidence of the universe's inflationary birth. The end of inflation was as dramatic as its beginning. When the inflaton field finally rolled down from its false vacuum state to its true minimum energy configuration, all that stored energy was rapidly converted into the hot, dense soup of particles and radiation that we associate with the traditional Big Bang. This process, called reheating, marked the transition from the inflationary epoch to the radiation-dominated era of the early universe. Inflation didn't replace the Big Bang, it preceded it, setting the stage for everything that followed. The hot, dense conditions we think of as characterizing the Big Bang were actually the aftermath of inflation, the result of the inflating field's energy being converted into matter and radiation. In this view, the Big Bang wasn't the beginning of the universe, but rather a specific moment in its evolution, the moment when inflation ended and the more familiar physics of the expanding, cooling universe began. What makes inflation theory so compelling is how it connects the quantum world with the cosmic scale in the most direct way possible. The same quantum mechanics that governs atoms and particles also shape the universe on its largest scales. Quantum fluctuations that occurred on scales smaller than atomic nuclei grew to become the scaffolding upon which galaxies formed. The theory suggests that our entire observable universe might be just one small patch of a much larger cosmos, with countless other regions undergoing their own inflationary epochs, perhaps with different physical laws and constants. This vision of eternal inflation paints a picture of a multiverse where inflation never truly ends globally, but instead continues to create new regions of space while ending locally in regions like ours. Each ending of inflation creates a new bubble universe with its own Big Bang, its own laws of physics, and its own evolutionary history. In this view, our universe is just one bubble in an infinite cosmic foam, shaped by the same quantum processes that govern the smallest scales of reality. General relativity. Picture spacetime not as an empty stage where cosmic events unfold, but as a dynamic, flexible fabric that bends and curves in response to the presence of mass and energy. This is the revolutionary vision that Albert Einstein gave us with general relativity. The idea that gravity is not a force pulling objects together, but the curvature of spacetime itself, guiding the motion of everything within it. This elegant theory transformed our understanding of the universe from Newton's clockwork cosmos to a dynamic, interconnected reality where space and time themselves become active participants in the cosmic dance. Einstein's insight began with a simple observation that would reshape physics. Someone falling freely doesn't feel their own weight. In a windowless elevator plummeting toward Earth, you would float weightlessly, unable to distinguish your situation from drifting in deep space far from any gravitational influence. This equivalence between acceleration and gravity became the foundation for a complete reimagining of how the universe works, suggesting that these apparently different phenomena are actually two aspects of the same underlying reality. This equivalence principle led Einstein to a profound realization. Gravity must be fundamentally different from other forces. While electromagnetic forces act between charged particles and nuclear forces operate within atomic nuclei, gravity affects everything equally. A feather and a hammer fall at the same rate in a vacuum, regardless of their composition or internal structure. This universality suggested to Einstein that gravity isn't really a force at all, but something more fundamental, the geometry of space-time itself. Mass and energy, Einstein realized, curve the fabric of space-time around them, creating wells and hills in the geometry of reality. The more massive an object, the deeper the well it creates in space-time. The sun doesn't pull the Earth toward it through some mysterious force acting across empty space. Instead, the sun's enormous mass creates a depression in space-time, and the Earth simply follows the straightest possible path through this curved geometry. We call that path an orbit, but from the perspective of space-time geometry, the Earth is traveling in a perfectly straight line through curved space. This geometric interpretation of gravity reveals itself in countless ways throughout the universe. When light passes near a massive object, it follows the curvature of space-time, bending its path in a phenomenon called gravitational lensing. Distant galaxies become cosmic telescopes, their gravity focusing light from even more distant objects and allowing us to see deeper into space than would otherwise be possible. The gravity of galaxy clusters can create multiple images of background galaxies, stretching and distorting their light into arcs and rings that map the invisible distribution of dark matter. The curvature of spacetime creates what we perceive as the flow of time itself, Near massive objects, time runs more slowly relative to regions of weaker gravity. A clock on the surface of the sun would tick measurably slower than an identical clock floating in empty space. This gravitational time dilation isn't just theoretical. GPS satellites must account for these relativistic effects, or they would accumulate errors of several miles per day in their position calculations. The satellite's atomic clocks run slightly faster than identical clocks on Earth's surface because they experience weaker gravity in their orbital positions. Einstein's field equations describe this relationship between matter, energy, and space-time curvature with mathematical elegance that borders on poetry. They show how the presence of mass energy tells space-time how to curve, while the curvature of space-time tells matter how to move. It's a beautiful, self-consistent dance between geometry and physics that governs everything from the fall of an apple to the expansion of the universe itself. The equations are remarkably compact. They can be written in just a few lines, yet they contain within them the entire description of gravitational phenomena, from planetary orbits to black holes to the evolution of the cosmos. General relativity makes predictions that seem almost magical, yet have been confirmed with extraordinary precision. It tells us that accelerating masses should create ripples in space-time itself, gravitational waves that travel at the speed of light, carrying energy across the cosmos like waves on a pond. For decades, these remain theoretical curiosities, predicted by the equations but beyond our ability to detect directly. That changed in 2015, when the LIGO detectors finally observed gravitational waves directly, capturing the tiny space-time distortions created by two black holes spiraling into each other and merging in a cosmic collision that occurred over 1 billion years ago. The waves stretched and compressed space itself by less than 1/10,000th the width of a proton, yet sensitive interferometers could detect these infinitesimal changes in the length of their arms. These observations opened an entirely new window on the universe, allowing us to study cosmic events that are invisible to light-based telescopes. Perhaps most dramatically, general relativity predicts the existence of black holes, regions where space-time curvature becomes so extreme that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. Inside a black hole, the normal relationship between space and time breaks down completely. Time effectively stops at the event horizon from the perspective of outside observers, while space itself becomes time-like inside the black hole, with all paths leading inexorably toward the central singularity. Black holes represent the ultimate fusion of space, time, and gravity. They are not empty holes in space, but rather regions where space-time curvature becomes infinite, where the very concepts of distance and duration lose their familiar meanings. At the center of each black hole lies a singularity, a point of infinite density and curvature, where the laws of physics as we understand them break down. These cosmic monsters can contain the mass of millions or billions of suns compressed into regions smaller than our solar system. The theory also describes how the universe itself can expand, something that initially troubled Einstein so much that he introduced a cosmological constant, a kind of anti-gravity that would keep the universe static. When observations later confirmed that the universe is indeed expanding, Einstein called this modification his greatest blunder. Ironically, recent discoveries suggesting that cosmic expansion is accelerating have renewed interest in the cosmological constant as a possible explanation for dark energy. General relativity reveals that the expansion of the universe isn't like an explosion throwing matter outward through pre-existing space. Instead, space itself is expanding, carrying galaxies apart, not through their motion, but through the growth of the space-time between them. This expansion creates the Hubble flow we observe, where distant galaxies recede from us at speeds proportional to their distance, not because they're moving through space, but because space itself is growing. The theory describes a universe far stranger and more wonderful than Newton's clockwork cosmos. In Einstein's universe, space and time are malleable, subject to the influence of matter and energy. Massive objects don't just exist in space-time, they actively shape it, creating the curved geometry that guides the motion of everything around them. the fabric of reality itself becomes dynamic, capable of stretching, compressing, and rippling in response to the cosmic events that unfold within it. General relativity has passed every experimental test thrown at it over more than a century, from the precise advance of Mercury's orbit around the Sun to the detection of gravitational waves from cosmic collisions. It describes the GPS satellites orbiting overhead and the supermassive black holes lurking at the centers of galaxies with equal precision. The theory reveals a universe where geometry becomes physics, where the shape of space-time determines the motion of matter, and where the very fabric of reality dances to the rhythm of mass and energy in an elegant cosmic choreography that continues to inspire and amaze us with its mathematical beauty and physical insight. Quantum mechanics. Beneath the familiar world of solid objects and predictable motions lies a realm that defies our everyday intuition. A quantum universe where particles exist in multiple states simultaneously, where the very act of observation changes reality, and where objects separated by vast distances can be mysteriously connected in ways that challenge our basic understanding of space, time, and causality. Quantum mechanics reveals that the foundation of everything we see and touch operates according to rules so strange they seem more like magic than science. Yet these bizarre principles govern the behavior of atoms, molecules, and the fundamental particles from which all matter is built. At the quantum scale, certainty gives way to probability in the most fundamental way imaginable. An electron doesn't orbit an atomic nucleus like a tiny planet following a definite path through space. Instead, it exists in a cloud of possibilities, simultaneously occupying all permitted positions around the nucleus until the moment we try to measure its location. This isn't because our instruments aren't precise enough to track its motion. It's the fundamental nature of reality itself. The electron literally doesn't have a definite position until we observe it, existing instead in what physicists call a superposition of all possible positions. This concept of superposition extends far beyond simple position measurements. Quantum particles can be in multiple states at once in ways that boggle the mind. A photon can pass through two slits simultaneously, creating an interference pattern that's only possible if it somehow took both paths at the same time. A quantum particle can spin clockwise and counterclockwise simultaneously, existing in what physicists call a superposition of spin states. An atom can be in an excited state and its ground state at the same time, radiating and not radiating energy simultaneously until measurement forces it to choose. The mathematics of quantum mechanics describes these superpositions with wave functions, mathematical objects that encode all the possible states of a quantum system and the probability of observing each state upon measurement. These wave functions evolve according to Schrödinger's equation, which governs how quantum possibilities change over time. The wave function contains complete information about a quantum system, yet it describes not definite properties, but rather probability amplitudes for various measurement outcomes. The act of measurement itself becomes profound and mysterious in quantum mechanics. Before observation, a quantum system exists in all possible states described by its wave function, with each possibility having a certain probability amplitude. The moment we make a measurement, this superposition collapses into a single, definite outcome, chosen randomly according to the probabilities encoded in the wave function. It's as if reality is fundamentally probabilistic, with the act of observation somehow playing a crucial role in determining which possibility becomes actual. This measurement problem remains one of the deepest puzzles in quantum theory. What exactly constitutes a measurement? How does the quantum world of superpositions transition to the classical world of definite outcomes? Various interpretations of quantum mechanics offer different answers. Some suggest that consciousness plays a special role. Others propose that measurement simply reveals pre-existing properties, while still others argue that all possible outcomes actually occur, branching into parallel universes. Perhaps the most mysterious aspect of quantum mechanics is entanglement, what Einstein famously called spooky action at a distance. When two particles become entangled through interaction, they remain connected in a way that transcends space and time. Measuring the properties of one particle instantly determines the properties of its entangled partner, regardless of how far apart they are. Change the spin of one entangled electron, and its partner will immediately reflect that change, even if it's on the other side of the galaxy. This quantum entanglement has been verified countless times in laboratories around the world, yet it challenges our basic understanding of locality and causality. Information seems to travel instantaneously between entangled particles, yet no signal actually passes between them. Instead, they share a quantum state that exists in a realm beyond classical space and time. The particles aren't communicating in any conventional sense. They are two aspects of a single quantum system that can't be fully described by looking at each part separately. Einstein, Podolsky, and Rosen famously argued that quantum mechanics must be incomplete because it seemed to allow these instantaneous correlations between distant particles. They proposed that hidden variables must exist to explain these correlations without requiring faster-than-light communication. However, John Bell's theorem and subsequent experiments have shown that no theory based on local hidden variables can reproduce the predictions of quantum mechanics, confirming that entanglement really does involve non-local correlations that defy classical intuition. Quantum mechanics also introduces the uncertainty principle, formulated by Werner Heisenberg, which states that certain pairs of properties cannot be measured simultaneously with perfect precision. The more accurately you know a particle's position, the less accurately you can know its momentum, and vice versa. This isn't a limitation of our measuring instruments or techniques. It's a fundamental feature of reality. At the quantum level, the universe itself is uncertain, with some combinations of properties simply not having definite values simultaneously. The uncertainty principle has profound implications for our understanding of the physical world. It means that the classical notion of a particle having definite position and momentum at all times is fundamentally incorrect. Instead, particles exist in states of inherent uncertainty, with their properties only becoming definite through the process of measurement. This principle also gives rise to zero-point energy. Even at absolute zero temperature, quantum systems retain some residual energy due to their fundamental uncertainty. The wave-particle duality shows us that quantum objects are neither purely waves nor purely particles, but something more fundamental that can exhibit either characteristic, depending on how we choose to observe them. Light behaves as a wave when we're not looking at individual photons, creating interference patterns and exhibiting the continuous properties we associate with waves. But when we detect light one photon at a time, it behaves as discrete particles, striking detection screens at specific points like tiny bullets. This duality extends to all matter, not just light. Electrons create interference patterns like waves when passed through double slits, yet they strike detection screens at discrete points like particles. Even large molecules have been shown to exhibit wave-like properties under the right conditions, with interference experiments successfully performed using molecules containing hundreds of atoms. The boundary between the quantum and classical worlds remains one of the most fascinating areas of ongoing research. Quantum tunneling allows particles to pass through barriers that should be impenetrable according to classical physics. A particle with insufficient energy to climb over a potential barrier can simply appear on the other side, as if it tunneled through solid matter. This effect is crucial for many fundamental processes. It powers the nuclear fusion reactions in stars by allowing protons to overcome their electrical repulsion. And it makes possible the transistors and other semiconductor devices that form the foundation of all modern electronics. The quantum world also reveals the participatory nature of reality in ways that challenge our traditional subject-object distinction. The universe isn't just a collection of objects with definite properties waiting to be discovered. It's a web of possibilities that crystallize into definite outcomes through the process of observation and measurement. We're not just passive observers of reality. We're participants in its creation, collapsing quantum possibilities into the classical world we experience every day. What makes quantum mechanics so beautiful, despite its strangeness, is how it reveals the deep unity underlying the apparent diversity of the physical world. All matter is built from a small number of quantum particles, following the same fundamental rules. The same quantum principles that govern the behavior of electrons and atoms also determine the properties of superconductors, the emission of light from stars, and the quantum computers that may revolutionize technology. The quantum realm shows us a universe that is far more subtle, interconnected, and wonderful than our everyday experience might suggest, where possibility and actuality, observer and observed, and here and there, are woven together in ways that continue to challenge and inspire our understanding of the nature of reality itself. The standard model of particle physics. Deep within every atom, beyond the reach of the most powerful microscopes, lies a hidden architecture of reality, built from a surprisingly small number of fundamental building blocks. The standard model of particle physics is our best map of this subatomic realm, a theoretical framework that describes all known matter, and 3 of the 4 fundamental forces with extraordinary precision, revealing the elegant simplicity that underlies the apparent complexity of the universe. At the heart of the standard model are the elementary particles, the true indivisible components of matter. There are 12 matter particles called fermions, divided into 2 families. 6 of these are quarks, which are never found alone in nature, but are always bound together to form the protons and neutrons that make up atomic nuclei. The other 6 are leptons, including the familiar electron, plus its heavier cousins and the ghostly neutrinos that barely interact with ordinary matter. The quarks have whimsical names that belie their fundamental importance. The up and down quarks are the most common, combining in groups of 3 to form protons and neutrons. 2 up quarks and 1 down quark make a proton, while 2 down quarks and 1 up quark make a neutron. These are the only quarks found in ordinary matter, but high-energy collisions can create the heavier charm, strange top and bottom quarks, which quickly decay back into the lighter varieties. The strong force that binds quarks together has properties unlike any other force in nature. While most forces become weaker with distance, the force between quarks actually becomes stronger as they're pulled apart, like a rubber band that gets stiffer as you stretch it. This leads to a phenomenon called confinement. Individual quarks can never be isolated because the energy required to separate them eventually becomes so large that it creates new quark-antiquark pairs from the vacuum itself. The 6 leptons include the electron, which orbits atomic nuclei and flows through wires as electric current, along with its heavier cousins, the muon and toll. Each of these charged leptons has an associated neutrino, the electron neutrino, muon neutrino, and toll neutrino. These neutrinos are among the most abundant particles in the universe, yet they interact so weakly with matter that trillions pass through your body every second without you noticing, most of them born in the nuclear furnace at the center of the sun. These matter particles are organized into 3 generations, each containing 2 quarks and 2 leptons, with similar properties but increasing masses. The first generation contains the particles that make up ordinary matter, the up and down quarks that form protons and neutrons, plus electrons and electron neutrinos. The second and third generations contain heavier versions that quickly decay into first-generation particles, appearing only in high-energy collisions or cosmic ray interactions. Binding these matter particles together are the force-carrying particles called bosons. The photon carries the electromagnetic force, allowing charged particles to attract and repel each other and giving us light, radio waves, and all electromagnetic radiation. The W and Z bosons carry the weak nuclear force, responsible for certain types of radioactive decay, and the nuclear reactions that power stars. 8 different gluons carry the strong nuclear force, binding quarks together with increasing strength over distance. The electromagnetic force governs not just magnets and electric circuits, but the very structure of atoms and molecules. The attraction between positively charged atomic nuclei and negatively charged electrons creates atoms, while the sharing of electrons between atoms creates chemical bonds. Every biological process, from photosynthesis to neural firing, ultimately depends on electromagnetic interactions. The weak force governs many nuclear processes that power stars. In the sun's core, protons fuse together to form helium. But this requires one proton to transform into a neutron through weak force interactions. Without the weak force, the sun would be a cold, dark ball of hydrogen, and the heavy elements necessary for planets and life would never have been created. At the quantum level, these forces work through the constant exchange of virtual particles, ephemeral bosons that pop into existence just long enough to carry force between matter particles before disappearing back into the quantum vacuum. This reveals that empty space isn't actually empty at all, but seethes with quantum activity as virtual particles continuously appear and vanish. The crowning achievement of the Standard Model was the prediction and discovery of the Higgs boson, the particle associated with the Higgs field that permeates all of space and gives mass to other particles. Before the Higgs mechanism was understood, it was a mystery why some particles have mass while others, like photons, are massless. The Higgs field provides the answer. Particles that interact strongly with this field acquire large masses, while particles that barely interact with it remain nearly massless. The discovery of the Higgs boson at the Large Hadron Collider in 2012 completed the Standard Model and confirmed our understanding of how particles acquire mass. The Higgs field is unlike any other field because it has a non-zero value everywhere in space, even in empty vacuum. The strength of each particle's interaction with the Higgs field determines its mass. Electrons interact weakly and have small masses, while the top quark interacts very strongly and has a mass nearly 200 times larger than a proton. What makes the Standard Model truly beautiful is its mathematical elegance and predictive power. Despite describing phenomena ranging from individual electrons to stellar nuclear processes, the entire theory can be written in a single equation that captures the essence of three fundamental forces in all known matter particles. This compact formula encapsulates our deepest understanding of matter and energy, revealing the mathematical harmony underlying the physical universe. The Standard Model has been tested to extraordinary precision over half a century. It predicted the existence of several particles years before they were discovered, including the charm quark, W and Z bosons, top quark, tau neutrino, and finally the Higgs boson. The theory's predictions match experimental observations to many decimal places, making it one of the most successful theories in science. Yet the Standard Model is clearly incomplete. It doesn't include gravity, doesn't explain dark matter or dark energy, and leaves fundamental questions unanswered about why there are three generations of particles, or why they have their specific masses. Despite these limitations, the model represents a remarkable achievement, showing us that the incredible diversity of the physical world emerges from interactions of a small number of fundamental particles following relatively simple rules. The Standard Model reveals the universe as a cosmic symphony, with particles playing assigned roles according to quantum field theory. Quarks and gluons create the stable rhythms of atomic nuclei. Electrons and photons weave the melodies of chemistry and electromagnetism, while neutrinos provide subtle background harmony. The Higgs field acts like a conductor, giving each particle its proper mass and ensuring that the symphony of matter can exist at all, connecting us to the deepest levels of reality and revealing our place in the cosmic order. Dark matter. Throughout the vast expanse of the universe, an invisible architect silently shapes the cosmic landscape. Dark matter, a mysterious form of matter that neither emits nor absorbs light, makes up roughly 85% of all matter in existence. Yet it reveals itself only through its gravitational influence on the visible matter we can see. This ghostly substance forms the scaffolding upon which galaxies are built, the invisible foundation that allows the cosmic structures we observe to exist at all. The story of dark matter begins with a Swiss astronomer named Fritz Zwicky, who in the 1930s was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. When he calculated how fast these galaxies were moving within the cluster, he discovered something startling. They were moving so quickly that the gravity from all the visible matter in the cluster should not have been strong enough to hold them together. The galaxies should have been flung apart long ago, scattered across the universe like sparks from a cosmic firework. Yet there they were, serenely orbiting within the cluster, as they had for billions of years. Zwicky realized that there must be far more matter present than meets the eye, invisible matter that provides the additional gravitational pull needed to keep the cluster intact. He called this mysterious component dark matter, and his discovery would eventually revolutionize our understanding of the universe's composition. For decades, Zwicky's observations remained a curious footnote in astronomy. Then, in the 1970s, astronomer Vera Rubin made observations that would confirm and expand upon his findings. She studied the rotation curves of spiral galaxies, measuring how fast stars orbit around galactic centers at different distances. According to Newton's laws, stars farther from the center should orbit more slowly, just as the outer planets in our solar system take longer to complete their orbits than the inner planets. But Rubin's observations revealed something unexpected. Stars in the outer regions of galaxies were moving just as fast as those closer to the center, sometimes even faster. This flat rotation curve suggested that there must be additional mass distributed throughout each galaxy, invisible mass that extends far beyond the visible disk of stars and gas. Without this dark matter, the outer stars would have been flung out into intergalactic space eons ago. Dark matter appears to form vast halos around galaxies, extending far beyond their visible boundaries. These halos can contain 10 times more mass than all the stars, gas, and dust we can observe. Computer simulations show that without dark matter, galaxies as we know them simply could not have formed. The early universe would have remained a nearly uniform sea of hydrogen and helium, with only the tiniest fluctuations that would have taken far longer than the age of the universe to grow into the rich cosmic structures we see today. Instead, dark matter provided the gravitational seeds that allowed cosmic structure to form. In the early universe, dark matter began clumping together under its own gravity, creating invisible scaffolding that ordinary matter could then fall into. These dark matter halos acted like cosmic construction sites, gathering hydrogen and helium gas until it became dense enough to form the first stars and galaxies. Every galaxy we see today sits nestled within a massive halo of dark matter that extends far beyond the realm of visible light. The evidence for dark matter extends beyond individual galaxies to the largest scales of cosmic structure. When we map the distribution of galaxies across billions of light years, we see a cosmic web of filaments and clusters separated by vast empty voids. This large-scale structure matches perfectly with computer simulations that include dark matter, but fails to reproduce the observed patterns when dark matter is removed from the models. Gravitational lensing provides some of the most compelling evidence for dark matter's existence. When light from distant galaxies passes near massive clusters of dark matter, the gravity bends and distorts the light, creating arcs and multiple images of background galaxies. By studying these distortions, astronomers can map the distribution of dark matter in galaxy clusters, revealing its presence even where no visible matter exists. Perhaps the most dramatic evidence comes from colliding galaxy clusters, where dark matter and ordinary matter behave differently during cosmic collisions. In the famous Bullet Cluster, two galaxy clusters collided at tremendous speeds. The ordinary matter, in the form of hot gas, was slowed down by electromagnetic interactions and remains near the collision site. But the dark matter, which interacts only through gravity, passed right through the collision relatively unaffected, separating from the ordinary matter and revealing itself through gravitational lensing. Despite overwhelming evidence for its existence, the nature of dark matter remains one of the greatest mysteries in physics. It cannot be made of ordinary atoms and protons, because we would have detected the radiation from Big Bang nucleosynthesis that such matter would produce. Instead, dark matter appears to consist of exotic particles that interact very weakly with ordinary matter, making them nearly impossible to detect directly. Leading candidates include weakly interacting massive particles, or WIMPs, which would have been created in the early universe and survived to the present day. These hypothetical particles would rarely interact with ordinary matter, passing through planets and stars like ghosts, yet their collective gravity would shape cosmic structure on the largest scales. Underground detectors around the world are searching for the rare occasions when a WIMP might collide with an atomic nucleus. But so far, these elusive particles have remained hidden. Other possibilities include axions, extremely light particles that could fill the universe in enormous numbers, or sterile neutrinos, heavier cousins of the familiar neutrinos that might decay and produce detectable radiation. Some theories even suggest that dark matter might be composed of primordial black holes, remnants from the very early universe that are too small to detect individually, but collectively provide the missing mass. The search for dark matter has become one of the most active areas of research in physics and astronomy. Particle accelerators like the Large Hadron Collider attempt to create dark matter particles in high-energy collisions, while space-based telescopes search for the faint radiation that might be produced when dark matter particles annihilate each other. Each approach offers a different window into the dark sector of physics that makes up most of our universe's matter. What makes dark matter truly beautiful as a scientific concept is how it reveals the hidden architecture of the cosmos. Like a master sculptor working with invisible clay, dark matter shapes the universe on scales from individual galaxies to the cosmic web itself. It reminds us that the universe is far stranger and more complex than our eyes alone can reveal, filled with components that influence cosmic evolution in profound ways despite remaining hidden from direct observation. Dark matter also highlights the interconnected nature of cosmic evolution. The same invisible particles that were created in the first moments after the Big Bang continue to influence the formation of stars and planets today. The galaxy that contains our solar system, the Milky Way, sits within a vast halo of dark matter that extends hundreds of thousands of light years beyond the farthest visible stars. In a very real sense, we live within dark matter, surrounded by this invisible component that helped create the cosmic conditions necessary for our existence. Dark energy. In the late 1990s, two teams of astronomers set out to measure how the expansion of the universe was slowing down. Using distant supernovae as cosmic lighthouses, they expected to find that gravity had been gradually putting the brakes on cosmic expansion ever since the Big Bang. Instead, they made one of the most shocking discoveries in the history of science. The universe is not slowing down at all, but is actually accelerating its expansion at an ever-increasing rate. This unexpected finding revealed the existence of dark energy, a mysterious component that now appears to make up about 68% of everything in the universe. The discovery came from studying Type Ia supernovae, the explosive deaths of white dwarf stars that serve as standardized candles for measuring cosmic distances. These supernovae all reach roughly the same peak brightness when they explode, allowing astronomers to determine how far away they are by comparing their apparent brightness to their known absolute brightness. By measuring both the distance to these supernovae and their redshift, how much their light has been stretched by cosmic expansion, astronomers can trace the expansion history of the universe. What they found defied all expectations. The distant supernovae appeared dimmer than they should have if the universe's expansion had been steadily slowing down. This meant that these ancient explosions were farther away than predicted, indicating that space itself had expanded more than anticipated in the billions of years since their light began its journey to Earth. The universe was not only expanding, but its expansion was accelerating. This acceleration requires a repulsive force that works against gravity on cosmic scales. Unlike the attractive force of gravity that pulls matter together, this mysterious dark energy appears to push space itself apart, causing the fabric of the universe to stretch at an ever-increasing rate. The more space expands, the more dark energy comes into existence, creating a feedback loop that drives accelerated expansion. Einstein had actually predicted the possibility of such a force in his equations of general relativity. In 1917, he introduced the cosmological constant, a term that would provide a repulsive force to balance gravity and keep the universe static. When observations later showed that the universe was expanding, Einstein abandoned the cosmological constant, reportedly calling it his greatest blunder. The discovery of dark energy suggests that Einstein's blunder may have been prophetic after all. The simplest explanation for dark energy is that it represents the energy density of empty space itself, the quantum vacuum. According to quantum field theory, even completely empty space is not truly empty, but seethes with virtual particles that constantly pop in and out of existence. These quantum fluctuations should contribute to the energy density of space, creating a cosmological constant that drives cosmic acceleration. However, when physicists calculate the expected energy density of the quantum vacuum, they get a result that is larger than the observed dark energy density by a factor of 10 to the power of 120. a discrepancy so enormous that it represents one of the worst predictions in the history of physics. This suggests that either our understanding of quantum field theory is fundamentally flawed, or that some unknown mechanism almost perfectly cancels out the vacuum energy, leaving behind only the tiny residue we observe as dark energy. Alternative explanations propose that dark energy might not be constant, but could instead be a dynamic field that changes over time. This hypothetical field, sometimes called quintessence after the fifth element of ancient philosophy, would have its own energy density that could increase or decrease as the universe evolves. If quintessence exists, the rate of cosmic acceleration might change in the future, potentially leading to dramatically different evolutionary paths for the universe. Dark energy's effects become apparent only on the largest scales, where its repulsive influence can overcome the attractive force of gravity. Within galaxies and galaxy clusters, gravity remains dominant, keeping these structures bound together despite the acceleration of space around them. But on scales larger than about 100 million light-years, dark energy takes control, driving cosmic structures apart and making it increasingly difficult for new large-scale structures to form. The discovery of dark energy has profound implications for the ultimate fate of the universe. If dark energy continues to accelerate expansion at its current rate, the universe will enter a phase of exponential growth similar to cosmic inflation. Over billions of years, this will stretch space so rapidly that distant galaxies will disappear beyond our cosmic horizon, their light unable to reach us across the ever-expanding gulf of space. In this scenario, our local group of galaxies, including the Milky Way and Andromeda, will become increasingly isolated as all other galaxies fade from view. Eventually, even the cosmic microwave background radiation will be stretched to such long wavelengths that it becomes undetectable. Future astronomers in this far distant epoch might have no evidence that other galaxies ever existed, living in a cosmos that appears to contain only their own small island of stars. If dark energy continues to strengthen over time, as some models suggest, the ultimate outcome could be even more dramatic. In a scenario called the Big Rip, the acceleration of space would eventually become so extreme that it overcomes all other forces. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, and finally atoms themselves would be ripped apart as space expands faster than light can travel between subatomic particles. However, dark energy might not remain constant forever. It could weaken over time, allowing gravity to eventually halt and reverse cosmic expansion in a big crunch. Alternatively, dark energy might oscillate, creating cycles of expansion and contraction that could repeat indefinitely. The true nature of dark energy and its future behavior remains one of the deepest mysteries in cosmology. Current observations suggest that dark energy began to dominate the universe's expansion relatively recently in cosmic history, roughly 5 billion years ago. Before that time, matter and radiation provided enough gravitational attraction to slow the expansion, but as the universe grew larger and matter became more dilute, the constant energy density of dark energy eventually won out and began accelerating expansion. This timing is not coincidental, but reflects the changing balance between different components of the universe. In the very early universe, radiation dominated and expansion slowed rapidly. Later, matter took over and expansion continued to slow, but more gradually. Finally, as matter became diluted by expansion, dark energy became the dominant component and acceleration began. We happen to live at the transition point between these cosmic epochs, in the first era, when dark energy has gained control of the universe's fate. The study of dark energy has opened new windows into fundamental physics, suggesting that our understanding of space, time, and energy remains incomplete. It may require new theories that go beyond Einstein's general relativity, or it might reveal new sectors of physics that operate only on cosmic scales. Like dark matter, dark energy demonstrates that the universe is far stranger and more complex than our everyday experience suggests. What makes dark energy beautiful as a scientific concept is how it connects the smallest and largest scales of physics. Quantum mechanics and cosmology, two of the most successful theories in science, come together in the attempt to understand this mysterious component. Dark energy also highlights the dynamic nature of the universe itself, showing us that space is not a passive stage for cosmic events, but an active participant that can stretch, accelerate, and shape the destiny of everything within it. The Cosmological Principle. When we look up at the night sky from Earth, we see a universe that appears highly structured and varied. The moon dominates our local view, the sun provides our daily rhythm, and the stars form distinctive patterns that have guided human navigation for millennia. Our planet orbits an unremarkable star in the spiral arm of a galaxy containing hundreds of billions of other stars. Yet underlying this apparent complexity and hierarchy lies one of the most profound and beautiful assumptions in cosmology, the Cosmological Principle, which states that, on the largest scales, the universe looks fundamentally the same everywhere and in every direction. This principle embodies two key concepts that revolutionized our understanding of the cosmos. The first is homogeneity, the idea that the universe has the same properties at every location when viewed on sufficiently large scales. The second is isotropy, the concept that the universe looks the same in every direction from any given point. Together, these assumptions suggest that there is no special place in the universe, no cosmic center or edge, and no preferred direction that makes one part of the cosmos fundamentally different from another. The Cosmological Principle represents a radical departure from humanity's historical view of our place in the universe. For most of human history, Earth was considered the center of creation, with all celestial objects revolving around our world in perfect cosmic harmony. Even after Copernicus displaced Earth from the center of the solar system, and even after we learned that our sun is just one star among many in a galaxy that is itself one among billions, the idea persisted that our location might still be somehow special or privileged. The Cosmological Principle suggests otherwise. It proposes that an observer in any galaxy, anywhere in the universe, would see essentially the same large-scale features that we observe from our vantage point in the Milky Way. They would see galaxies distributed in clusters and superclusters, separated by vast cosmic voids, forming a web-like structure that extends in every direction. They would observe the same cosmic microwave background radiation, the same expansion of space, and the same fundamental laws of physics operating throughout their observable universe. This uniformity becomes apparent only when we examine the universe on scales larger than about 300 million light-years. On smaller scales, the universe is clearly not homogeneous. Stars cluster into galaxies, galaxies cluster into groups and clusters, and these clusters form even larger structures called superclusters. But when we step back and look at volumes of space containing thousands of galaxy clusters, the distribution becomes remarkably uniform, like the smooth texture that emerges when you view a pointillist painting from a sufficient distance. The cosmic microwave background provides some of the strongest evidence for the Cosmological Principle. This ancient light, released when the universe first became transparent about 380,000 years after the Big Bang, appears almost perfectly uniform across the entire sky. The tiny temperature variations that do exist, fluctuations of only a few parts in 100,000, are consistent with the quantum fluctuations that seeded the formation of cosmic structure, rather than indicating any preferred direction or location in the universe. Large-scale galaxy surveys have confirmed the predictions of the Cosmological Principle by mapping the distribution of matter across billions of light-years. Projects like the Sloan Digital Sky Survey have charted the positions of millions of galaxies, revealing the cosmic web of filaments and voids that characterizes the universe's largest structures. When analyzed statistically, these surveys show that the universe becomes increasingly homogeneous on larger scales, exactly as the Cosmological Principle predicts. The principle also underlies our understanding of cosmic expansion. If the universe were not homogeneous and isotropic, different regions would expand at different rates, and observers in different locations would measure different values for the Hubble constant, the rate at which the universe is expanding. The fact that we observe a consistent expansion rate in all directions supports the idea that space itself is expanding uniformly, carrying all observers along with it in a way that preserves the homogeneous and isotropic nature of the cosmos. Einstein's theory of general relativity provides the mathematical framework for understanding how a homogeneous and isotropic universe behaves. The Friedmann equations, derived from Einstein's field equations under the assumptions of the cosmological principle, describe how such a universe can expand, contract, or remain static depending on its matter and energy content. These equations form the foundation of modern cosmology and have successfully predicted many observed features of our universe, from the rate of expansion to the abundances of light elements. The cosmological principle also has profound philosophical implications. It suggests that the laws of physics are universal, operating the same way everywhere in the cosmos. A hydrogen atom in a distant galaxy has exactly the same properties as a hydrogen atom on Earth, emitting and absorbing light at precisely the same wavelengths. This universality allows us to study distant objects and events using the same physical principles we discover in terrestrial laboratories. The principle implies that our observations of the universe from Earth provide a representative sample of cosmic properties. The galaxies we see around us, the cosmic background radiation we detect, and the expansion rate we measure are not unique to our location, but reflect the global properties of the universe as a whole. This gives us confidence that our cosmological models, based on observations from our single vantage point, accurately describe the entire observable universe. However, the cosmological principle is ultimately an assumption, not a proven fact. We can only observe the universe from one location, our position in the Milky Way galaxy, and we can only see light that has had time to reach us since the Big Bang. It's conceivable that the universe might be inhomogeneous, on scales larger than our observable horizon, or that we might inhabit an unusual region that happens to appear homogeneous locally, but is not representative of the universe as a whole. Some observations have challenged the strict application of the cosmological principle. The discovery of extremely large structures like the Great Wall of Galaxies and the Hercules Corona Borealis Great Wall raises questions about whether the universe truly becomes homogeneous on all observable scales. These structures appear to be larger than the scale at which homogeneity should emerge, suggesting that our understanding of cosmic structure formation might be incomplete. Additionally, some studies have suggested possible violations of isotropy in the cosmic microwave background, including alignments between temperature fluctuations and the geometry of the solar system that would be highly unlikely if the principle held exactly. While these results remain controversial and may have prosaic explanations, they highlight the importance of continually testing our fundamental assumptions about the universe's structure. The cosmological principle also connects to broader questions about the nature of scientific explanation. It represents a kind of Copernican humility, suggesting that our location in the universe is not special or privileged. This assumption has proven remarkably successful in developing our understanding of cosmic evolution, from the Big Bang through the formation of structure to the accelerated expansion driven by dark energy. What makes the cosmological principle beautiful is its elegant simplicity and its profound implications for our understanding of cosmic democracy. It suggests that the universe is not only vast, but also fundamentally fair. No location or direction is preferred over any other. This principle transforms the bewildering complexity of the cosmic landscape into a comprehensible whole, allowing us to use observations from our single vantage point to understand the properties and evolution of the entire observable universe. The principle also reflects the power of statistical thinking in science. While individual regions of space may appear highly structured and complex, the ensemble behavior of the universe on the largest scales follows simple, universal patterns. Like the kinetic theory of gases, which explains the regular behavior of temperature and pressure despite the chaotic motion of individual molecules, the cosmological principle reveals order and predictability emerging from cosmic complexity through the power of large numbers and statistical averaging. The Multiverse Hypothesis. Beyond the edges of our observable universe, stretching infinitely in directions we cannot see, there may exist countless other universes, each with its own laws of physics, its own history, and its own destiny. The multiverse hypothesis suggests that our universe, with its particular values of physical constants, its specific arrangement of forces, and its unique evolutionary history, is just one member of an enormous ensemble of realities, each as valid and complete as our own. This idea emerges naturally from several different areas of modern physics and cosmology, each pointing toward the same startling conclusion. The cosmos may be far stranger and more vast than even our most ambitious theories had previously suggested. Rather than living in the universe, we may instead inhabit a universe, one temporary bubble of space-time, floating in an infinite sea of other realities. The most direct path to the multiverse comes from cosmic inflation, the theory that describes the exponential expansion of space in the first fraction of a second after the Big Bang. While inflation ended in our region of space nearly 14 billion years ago, allowing the hot, dense conditions we associate with the Big Bang to begin, the process may never have stopped everywhere. In the broader context of eternal inflation, new regions of space continue to undergo rapid expansion, while other regions, like ours, exit inflation and begin their more familiar evolutionary journey. Each region that exits inflation becomes a separate universe with its own Big Bang, its own expansion history, and potentially its own laws of physics. These pocket universes form like bubbles nucleating in a vast, inflating space, with each bubble representing a complete cosmos containing billions of galaxies, stars, and planets. The space between these universes continues to inflate exponentially, ensuring that they can never interact or communicate with each other. String theory, which attempts to unify quantum mechanics and general relativity, also points toward a multiverse. The theory requires extra dimensions beyond the familiar 3 dimensions of space and one, of a time. And the way these extra dimensions are compactified determines the laws of physics that emerge in our 4-dimensional world. The mathematics suggests there may be an enormous number of ways to compactify these extra dimensions, perhaps 10 to the power of 500 different possibilities or more. Each different compactification would produce a universe with different physical constants, different particles, and different forces. Some might have stronger gravitational forces, others might lack certain types of particles entirely, and still others might have different numbers of spatial dimensions. This vast landscape of possibilities means that string theory naturally predicts not just one universe, but an enormous collection of universes with every possible combination of physical laws. Quantum mechanics itself may require a multiverse through the many worlds interpretation, first proposed by Hugh Everett in 1957. In this view, every quantum measurement doesn't just reveal a single outcome by collapsing the wave function, but instead splits reality into multiple branches, with each possible outcome actually occurring in a different universe. When a quantum particle passes through a double slit, it doesn't choose one path or the other. It takes both paths, but in different branches of reality. This quantum multiverse would be constantly branching as countless quantum events occur throughout the cosmos. Every radioactive decay, every photon absorption, every quantum interaction would create new universes, leading to an exponentially growing tree of realities that encompasses every possible quantum outcome. In some branches, you decided to have coffee this morning instead of tea. In others, dinosaurs never went extinct. In still others, the laws of physics evolve slightly differently. The Anthropic Principle provides another perspective on why a multiverse might be necessary. Our universe appears to be fine-tuned for the existence of complexity in life, with physical constants that fall within narrow ranges that allow stars to form, heavy elements to be created, and stable atoms to exist. If any of these constants were significantly different, the universe would be a much simpler place, perhaps containing only hydrogen, or perhaps collapsing too quickly for structure to form. If only one universe existed, this fine-tuning would seem like an extraordinary coincidence requiring explanation. But in a multiverse containing every possible combination of physical constants, it becomes inevitable that some universes would have the right conditions for complexity in life. We necessarily find ourselves in one of these habitable universes, not because our universe is special, but because observers can only exist in universes that permit their existence. The multiverse hypothesis also emerges from certain solutions to Einstein's equations that describe black holes. When matter falls into a black hole, some theories suggest it doesn't simply disappear, but instead creates a new universe that expands away from our space-time. In this scenario, every black hole becomes the seed for a new cosmos, and our own Big Bang might have been the result of matter falling into a black hole in some parent universe. Different types of multiverse exist at different levels of reality. Level 1 multiverse refers to regions of space beyond our observable horizon that have the same laws of physics but different initial conditions. Level 2 includes regions produced by eternal inflation, where physical constants might be different. Level 3 encompasses the quantum many-worlds interpretation, where all possible quantum outcomes are realized. Level 4 represents the ultimate multiverse containing all mathematically possible universes. The Multiverse Hypothesis raises profound questions about the nature of scientific explanation and testability. If other universes are by definition unobservable from our vantage point, can the multiverse be considered a scientific theory at all? Critics argue that untestable ideas belong to philosophy rather than science, while supporters point out that many accepted theories make predictions about unobservable phenomena. Some indirect tests of multiverse theories may be possible. Cosmic inflation makes specific predictions about the patterns we should see in the cosmic microwave background, and these have been largely confirmed by observations. If eternal inflation is correct, it might leave subtle signatures in the polarization of this ancient light. Similarly, if our universe collided with another bubble universe in the past, this collision might have left detectable traces. What makes the multiverse hypothesis beautiful is its profound shift in perspective about our place in the cosmic order. Just as Copernicus showed that Earth is not the center of the solar system, and just as Hubble revealed that our galaxy is one among billions, the multiverse suggests that our entire universe might be just one among infinitely many. This represents the ultimate Copernican revolution, displacing not just our planet or our galaxy, but our entire reality from any special status. The multiverse also connects the smallest and largest scales of physics in unexpected ways. Quantum mechanical events occurring at subatomic scales might continuously create new universes, while the global structure of space-time determines which types of universes can exist. The hypothesis suggests that reality is far richer and more creative than we might have imagined, with nature exploring every possible combination of physical laws and initial conditions across an infinite ensemble of realities. If the multiverse exists, it means that every story that could be told is being told somewhere. Every possible history is unfolding in some universe, and every conceivable form of complexity and beauty is being realized across the vast expanse of realities. Our universe would be just one movement in an infinite cosmic symphony, beautiful and meaningful, not despite being one among many, but because it contributes its unique voice to the totality of existence. The Holographic Principle. In one of the most mind-bending insights of modern physics, the Holographic Principle suggests that all the information contained within any volume of space can be encoded on its boundary, like a cosmic hologram, where three-dimensional reality emerges from information stored on a two-dimensional surface. This revolutionary idea challenges our most basic intuitions about the nature of space, information, and reality itself, proposing that what we experience as a three-dimensional universe might actually be a projection from physics operating on a distant boundary. The principle emerged from deep investigations into the physics of black holes, those cosmic monsters where gravity becomes so strong that not even light can escape. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of the information content or disorder within a system. Surprisingly, this entropy is proportional not to the volume of the black hole, as one might expect, but to the area of its event horizon, the boundary beyond which nothing can escape. This was puzzling, because entropy typically scales with volume. A box twice as large can hold twice as many particles arranged in twice as many ways, so its entropy should be twice as large. But black holes seem to follow different rules, with their information content determined by their surface area rather than their interior volume. This suggested something profound about the relationship between space, information, and the fundamental structure of reality. The mystery deepened with Hawking's discovery that black holes actually emit radiation and slowly evaporate over time. This Hawking radiation appears to be perfectly thermal, carrying no information about what fell into the black hole. But this creates a paradox. If information that falls into a black hole is destroyed when the black hole evaporates, it would violate one of the fundamental principles of quantum mechanics, which states that information cannot be destroyed. The resolution to this paradox led to a revolutionary insight. Perhaps the information that falls into a black hole isn't actually stored in the interior volume at all, but is instead encoded on the event horizon itself. From this perspective, the three-dimensional interior of the black hole would be a kind of holographic projection of information stored on its two-dimensional boundary. The black hole would be like a cosmic hologram, where all the physics happening inside can be completely described by information encoded on its surface. Gerard 't Hooft and Leonard Susskind generalized this insight into the holographic principle, proposing that this phenomenon isn't unique to black holes, but applies to any region of space-time. All the information in any volume of space, every particle, every field, every quantum state, can in principle be encoded on the boundary of that volume. The three-dimensional physics we observe would emerge from more fundamental processes occurring on distant two-dimensional surfaces. The most concrete realization of this principle comes from the AD-S-C-F-T correspondence, discovered by Juan Maldacena in 1997. This remarkable mathematical relationship shows that certain theories of quantum gravity and curved spacetime are exactly equivalent to quantum field theories without gravity operating on the boundary of that space. It's as if the entire interior physics of a curved universe can be perfectly reproduced by very different physics operating only on its boundary. This correspondence isn't just a mathematical curiosity. It provides a concrete example of how holographic encoding works. Phenomena like black hole formation, gravitational waves, and even the emergence of space-time itself in the interior theory can be precisely calculated using the boundary theory, which involves no gravity at all. The bulk space-time, with all its curved geometry and gravitational dynamics, emerges as a holographic projection from quantum field theory on the boundary. The holographic principle suggests that space itself might be emergent rather than fundamental. Just as temperature emerges from the average motion of many particles, or pressure emerges from molecular collisions, the three-dimensional space we inhabit might emerge from more fundamental processes that don't involve space at all. The smooth geometric picture of space-time that we get from Einstein's general relativity would be an approximation that holds only when we don't look too closely at the underlying holographic structure. This has profound implications for our understanding of quantum gravity, the long-sought theory that would unify Einstein's general relativity with quantum mechanics. Instead of trying to quantize space-time directly, which has proven extraordinarily difficult, the holographic principle suggests we might need to think about quantum gravity as emerging from quantum field theories that live in fewer dimensions. The geometry of space-time would be encoded in the entanglement patterns and correlations of these boundary theories. Recent developments in quantum error correction have revealed deep connections between the holographic principle and the way information is processed and protected in quantum systems. The redundant encoding that makes quantum error correction possible bears striking resemblances to the way information is encoded holographically, suggesting that the holographic principle might be a fundamental feature of how information is stored and processed in quantum gravity. The principle also sheds new light on the nature of quantum entanglement, the mysterious correlations that can exist between separated quantum systems. In holographic theories, the entanglement structure of the boundary theory directly determines the geometry of the bulk spacetime. Regions that are highly entangled on the boundary correspond to regions that are connected by shortcuts through the bulk, while regions with little entanglement correspond to disconnected parts of spacetime. This connection between entanglement and geometry suggests that spacetime itself might be built from quantum entanglement. The smooth, continuous space described by Einstein's equations would emerge from the collective behavior of vast networks of quantum entanglement, much like the smooth flow of a fluid emerges from the collective motion of many molecules. In this view, space is not fundamental, but is rather an emergent property of quantum information. If our own universe is holographic, it would mean that all the complexity we observe, every star and planet, every living creature, every thought and emotion, could in principle be encoded on a distant two-dimensional surface. Our three-dimensional experience would be a projection from physics operating in fewer dimensions, like shadows cast by a higher dimensional reality onto the wall of our cosmic cave. Current research is exploring whether our universe shows signs of being holographic. Some theories suggest that if space-time is pixelated at the smallest scales, with discrete units of space and time, replacing the smooth continuum of classical physics, this granularity might be detectable in precision measurements of gravitational waves or particle interactions. Experiments are searching for these signatures of holographic space-time. What makes the holographic principle truly beautiful is how it reveals unexpected connections between seemingly disparate areas of physics. Black hole physics, quantum field theory, condensed matter physics, quantum information theory, and cosmology all come together in the holographic framework, suggesting deep underlying unities in the structure of physical law. Problems that seem intractable in one formulation often become solvable when translated into the holographic language. The principle represents one of the most profound shifts in our understanding of space, time, and information since the development of quantum mechanics and relativity. It suggests that reality might be far stranger than our everyday experience indicates, with the three-dimensional world we inhabit emerging from more fundamental processes operating in fewer dimensions, challenging our imagination and expanding our conception of what the universe might truly be. String theory. Imagine if everything you see around you, every atom, every particle, every force that shapes reality, was nothing more than music. Not music you can hear, but a symphony of vibrations so small and so fundamental that they exist at the very foundation of existence itself. This is the elegant proposition of string theory, perhaps the most beautiful attempt humanity has ever made to understand the deepest nature of our universe. For centuries, we've imagined the smallest building blocks of matter as tiny, indivisible points, like perfect mathematical dots with no size, no structure, just pure essence. But string theory whispers a different story. It suggests that these fundamental particles are not points at all, but incredibly tiny strings, so small that if an atom were the size of our solar system, these strings would be about the size of a tree on Earth. To put this in even starker perspective, these strings are so minuscule that they exist at what physicists call the Planck scale, where the very concepts of space and time begin to lose their familiar meaning. These strings exist in a realm beyond our everyday experience, vibrating in dimensions we cannot see or directly perceive. Just as a violin string can produce different notes depending on how it vibrates, creating the rich harmonies of a symphony through variations in frequency, amplitude, and resonance. These cosmic strings create different particles through their various modes of vibration. An electron emerges from one pattern of vibration, a photon from another, a quark from yet another. The entire periodic table, all the forces of nature, every interaction that makes stars burn and planets orbit, all of this complexity arising from the simple, elegant dance of vibrating strings. The mathematics behind string theory reveals layers of beauty that would make even the most accomplished composer weep with envy. Each string can vibrate in multiple ways simultaneously, creating harmonics that correspond to different particle properties. Mass, charge, and spin, the fundamental characteristics that define every particle, are simply different aspects of how these strings choose to dance. It's as if the universe is a vast orchestra, with each string playing its part in a cosmic symphony that has been performing for nearly 14 billion years. What makes this theory so captivating is not just its mathematical beauty, but the way it promises to unify everything. For decades, physicists have struggled with the fact that our two greatest theories, quantum mechanics, which governs the behavior of the very small, and general relativity, which describes gravity and the very large, seem incompatible at the deepest level. It's as if we have two perfect languages that cannot translate between each other, leaving us unable to describe what happens when quantum effects meet extreme gravity, such as inside black holes, or at the moment of the Big Bang. String theory offers the possibility of a single, harmonious framework where gravity and quantum mechanics finally speak the same tongue. In this unified language, gravity itself becomes just another vibration pattern, no more mysterious than electromagnetism or the nuclear forces. The graviton, the hypothetical particle that carries the gravitational force, emerges naturally from string vibrations, making gravity as quantum mechanical as any other force. The mathematics of string theory reveals something almost mystical about our universe. These strings don't just vibrate in the 3 dimensions of space we know, but in up to 11 dimensions total. Most of these extra dimensions are curled up so tightly that they're invisible to us, compactified into shapes so small that even our most powerful particle accelerators cannot probe them. It's like looking at a garden hose from a great distance. It appears one-dimensional, but up close reveals its hidden circular dimension wrapped around the visible length. The shape and size of these hidden dimensions determine which particles exist and how they interact, making our visible universe just one possible melody in a vast cosmic symphony. Different configurations of these extra dimensions would produce entirely different physics, different particles, different forces. Our universe, with its specific arrangement of matter and energy, represents just one possible composition in an infinite library of cosmic music. In string theory's vision, space and time themselves emerge from something more fundamental. The very fabric of reality is woven from these dancing strings, each one a thread in a tapestry so intricate that our 3-dimensional world is merely its shadow. It's a theory that transforms our understanding of emptiness itself. What we call the vacuum of space is actually alive with quantum strings, constantly appearing and disappearing, creating and annihilating in pairs, generating a subtle foam at the smallest scales of existence. This quantum foam suggests that, at the deepest level, space and time are not continuous but granular, made up of discrete units that constantly fluctuate. These fluctuations create virtual particles that pop in and out of existence, borrowing energy from the vacuum and paying it back so quickly that the transaction goes unnoticed by the larger universe. Yet these brief existences have real effects, contributing to forces and phenomena we can measure and observe. Perhaps most remarkably, string theory suggests that all the particles and forces we know might be just the lowest energy vibrations of these cosmic strings. Higher energy vibrations could correspond to particles and phenomena completely unknown to us, existing at energy scales far beyond our current ability to explore. It's possible that the universe is filled with a rich symphony of exotic particles and forces, all invisible to us simply because we lack the energy to excite the strings into their higher harmonic modes. Yet for all its mathematical elegance, string theory remains tantalizingly beyond experimental verification. The energies required to directly observe these fundamental strings are roughly 1 trillion times greater than what our most powerful particle accelerators can achieve. It's as if we're trying to hear a whisper in a thunderstorm or detect the flutter of a butterfly's wing from across an ocean. This experimental inaccessibility has led some critics to question whether string theory is truly science or simply beautiful mathematics masquerading as physics. But perhaps this criticism misses the profound shift that string theory represents in how we approach the deepest questions about reality. Throughout history, our most revolutionary insights have often preceded our ability to test them directly. Einstein's theories of relativity were initially beyond experimental reach, yet they fundamentally transformed our understanding of space, time, and gravity. Similarly, string theory may be laying the groundwork for discoveries that won't be testable for decades or centuries to come. The implications of string theory extend far beyond particle physics. If these vibrating strings are indeed the fundamental constituents of reality, then consciousness itself might emerge from their complex orchestrations. The thoughts flowing through your mind as you read these words, the emotions that color your experience, the very sense of being a unified self, all of this could be manifestations of the cosmic symphony playing out at the Planck scale. In this view, we are not separate observers of the universe, but rather intricate movements within its grand musical composition. Loop quantum gravity. While string theory imagines reality as music, loop quantum gravity proposes something equally profound, and perhaps even more radical, that space and time themselves are not the smooth, continuous fabric Einstein described, but rather something granular, woven from discrete loops smaller than anything we can imagine. It's as if the universe, when examined at its most fundamental level, reveals itself to be constructed from a kind of cosmic chainmail. each link representing the smallest possible unit of space and time. This theory emerges from a simple but revolutionary question that strikes at the heart of our understanding of reality. What if space itself has a smallest possible size? We're accustomed to thinking of space as infinitely divisible. You can always imagine cutting a distance in half, then in half again, forever, like a mathematical exercise that never ends. This assumption underlies much of classical physics and even our everyday intuition about the world around us. But loop quantum gravity suggests there's a fundamental limit, a smallest possible length called the Planck length, measuring approximately 10 to the power of minus 35 meters. To put this almost incomprehensible scale in perspective, this length is to a proton what a proton is to a person. If you could somehow magnify a proton to the size of a human being, the Planck length would still be the size of a proton relative to that magnified scale. It represents the point where quantum uncertainty becomes so large that the very notion of distance loses its classical meaning. At this microscopic scale, space becomes quantized, broken up into tiny, discrete units like pixels on a screen, but far more sophisticated. Unlike the simple square pixels of digital displays, these units of space are three-dimensional loops, twisted and connected in an intricate network that forms the very foundation of reality. These loops don't exist in space. They are space. They don't occur in time. They weave time itself through their connections and relationships, their interactions creating the flow of temporal progression we experience. The beauty of this theory lies in how it solves one of the deepest mysteries in physics: what happens at the center of a black hole, or at the moment of the Big Bang, where Einstein's equations break down and give infinite, meaningless answers. These infinities have plagued physicists for decades, representing places where our most successful theories simply fail to provide sensible predictions. Loop quantum gravity suggests that these infinities are artifacts of treating space and time as perfectly smooth, like mathematical idealizations that break down when pushed to their limits. When you account for the granular nature of space-time, when you recognize that space and time come in discrete, indivisible packages, these troublesome infinities disappear, replaced by quantum bounces and transitions that remain finite and calculable. It's similar to how the apparent paradoxes of dividing by zero disappear when you recognize that you're working with discrete quantities rather than continuous variables. In this view, the Big Bang wasn't the beginning of everything, but rather a big bounce, the moment when a previous universe, having collapsed under its own gravity into maximum compression, reached the Planck scale and quantum effects took over. At this point, the normal rules of gravity reverse, and instead of continuing to collapse, space-time itself rebounds like a cosmic spring, expanding into our current universe. The violent birth of our cosmos becomes gentler, more natural, a consequence of space-time's quantum nature rather than a mysterious singularity where physics breaks down completely. This big bounce scenario eliminates the need for the universe to emerge from literal nothingness, replacing that conceptual challenge with a cyclic model where universes collapse and rebound in an eternal dance of cosmic death and rebirth. Each bounce might produce a universe with slightly different properties, different physical constants, different arrangements of matter and energy, creating an infinite sequence of cosmic experimentation. The loops that make up space are in constant motion, connecting and disconnecting, merging and splitting, creating a dynamic web that underlies all of reality. Each loop carries information about the geometry of space in its immediate vicinity, encoding details about curvature, volume, and connectivity. It's as if each loop serves as both a building block and a librarian, storing and processing information about the local structure of space-time. Volume and area become quantized properties in this framework, existing only in specific discrete amounts, like energy levels in an atom. You cannot have arbitrary amounts of space, only specific quantized volumes that correspond to particular arrangements of loops. It's as if the universe keeps a precise quantum accounting of its own geometry, with each loop serving as both bookkeeper and building block, maintaining perfect records of spatial relationships. This quantization has profound implications for black holes. Instead of collapsing to infinite density, matter falling into a black hole reaches the Planck scale and rebounds, potentially creating a white hole on the other side. a region that explosively expels matter and energy. Black holes become cosmic recycling centers, taking in matter from one side and expelling it transformed on the other, maintaining the conservation laws of physics while eliminating the troublesome singularities. The theory paints a picture of reality that's both alien and beautiful. The smooth space-time of our everyday experience emerges from countless quantum loops, just as a smooth coastline emerges from countless grains of sand when viewed from sufficient distance. At the scale we experience, these discrete effects average out into the continuous space and time Einstein described, but at the deepest level, reality reveals its granular, quantized nature. This granularity might have observable consequences. Extremely sensitive measurements of space and time might reveal tiny fluctuations corresponding to the underlying loop structure. Gravitational waves, ripples in space-time itself, might carry subtle signatures of this quantum geometry, providing a window into the deepest structure of reality. The loops create a kind of cosmic background noise, a fundamental graininess to space-time that might someday be detectable by sufficiently advanced instruments. The theory suggests that at the deepest level, the universe is revealed as a vast, dynamic network, not unlike the neural networks in our brains or the web of connections that link our modern digital world, but far more fundamental, existing at the very foundation of space and time themselves. Each loop connects to its neighbors, creating patterns of information flow that give rise to the geometry and topology of space-time, making reality itself a kind of cosmic computation. The Anthropic Principle. Sometimes the most profound truths hide in the simplest observations. Look around you at the world, at the stars, at the very fact that you exist to contemplate these words. Your existence might seem ordinary, even inevitable, but it represents something extraordinary, a universe so precisely calibrated that the slightest change in its fundamental laws would make your existence, and indeed any form of complexity, utterly impossible. This observation forms the heart of the Anthropic Principle, a concept that has divided scientists and philosophers while revealing something deeply mysterious about our cosmic home. The principle emerges from a startling realization that has accumulated over decades of scientific discovery. The universe appears to be fine-tuned for life, with a precision that defies explanation through chance alone. The Anthropic Principle comes in two forms, each offering a different lens through which to view our place in existence. The weak Anthropic Principle simply states that we observe the universe to have properties compatible with our existence because, quite obviously, we wouldn't be here to observe it otherwise. It's a statement of selection bias on a cosmic scale, no more mysterious than noting that we find ourselves on a planet with liquid water and breathable atmosphere. Just as we shouldn't be surprised to discover ourselves in a habitable environment, we couldn't survive anywhere else. We shouldn't be surprised to find ourselves in a universe whose laws permit complex chemistry and stable stars. But the strong Anthropic Principle ventures into more controversial and philosophically challenging territory, suggesting that the universe must have properties that allow observers to exist. This isn't just about selection bias, it's about the universe seeming designed, fine-tuned with a precision that staggers the imagination and challenges our understanding of cosmic evolution. Consider the force that holds atomic nuclei together, known as the strong nuclear force. This fundamental interaction determines how protons and neutrons bind to form the elements that make up stars, planets, and living beings. If this force were just 5% weaker, deuterium, the heavy hydrogen isotope crucial for stellar fusion, couldn't form. Without deuterium, stars couldn't generate the heavy elements necessary for rocky planets and complex chemistry. The universe would contain only hydrogen and helium, forever sterile and simple. Conversely, if the strong force were 5% stronger, stellar fusion would proceed so rapidly that stars would burn out in millions rather than billions of years, never allowing sufficient time for the slow processes of planetary formation and biological evolution. The delicate balance of stellar nuclear fusion, which provides the stable energy sources necessary for life over cosmic timescales, depends critically on this precise calibration. The universe appears balanced on a knife's edge in numerous other ways. The electromagnetic force, which holds atoms together, and enables chemical bonding falls within a narrow range that permits stable atomic structures while allowing chemical reactions to proceed at reasonable rates. Too weak, and atoms couldn't form stable bonds to create complex molecules. Too strong, and chemical bonds would be so tight that molecular structures would be frozen, preventing the dynamic chemistry essential for life. The constants of nature, the strength of gravity, the mass of the electron, the rate of cosmic expansion, the cosmological constant, all seem carefully adjusted. Change any one of them by what seems like a tiny fraction, and the universe becomes a sterile place. The gravitational constant provides a particularly striking example. Too much gravity, and stars collapse immediately into black holes, never spending billions of years steadily fusing hydrogen into heavier elements. Too little gravity, and matter never clumps together to form stars at all, leaving the universe as a cold, diffuse gas expanding forever into darkness. The expansion rate of the universe itself falls within an incredibly narrow range that allows galaxies to form without either collapsing back on themselves or flying apart too quickly. If the initial expansion had been slightly slower, gravity would have halted and reversed the expansion before galaxies could form, leading to a big crunch within millions of years. If the expansion had been slightly faster, matter would have been diluted so quickly that gravitational attraction could never overcome the cosmic expansion to form stars and galaxies. Even more remarkably, the energy density associated with empty space, what physicists call the cosmological constant, appears to be fine-tuned to an almost incomprehensible degree. Quantum field theory predicts that this energy should be enormous, perhaps 120 orders of magnitude larger than what we observe. Such a large value would have prevented the formation of any structure in the universe. Yet, the observed value is just small enough to allow galaxy formation, while still driving the accelerated expansion we observe today. The precise masses of fundamental particles also seem carefully chosen. The difference in mass between protons and neutrons is just right to allow the formation of hydrogen while preventing all protons from decaying into neutrons. If this mass difference were slightly different, either direction, the universe would lack the stable hydrogen that fuels stars, or would be composed entirely of neutrons, incapable of forming the rich chemistry necessary for complexity. Some scientists find this fine-tuning evidence for a multiverse, an infinite collection of universes with different physical laws and constants. In this vast ensemble, every possible combination of physical parameters exists somewhere. We naturally find ourselves in one of the rare universes capable of supporting observers, not because our universe is special, but because we can only exist in the special ones, making our observations inevitably biased toward habitability. The Multiverse Hypothesis suggests that beyond our observable universe lies an infinite expanse of other cosmic regions, each with different physics. Some have gravity too strong for stars to form, others expand too quickly for galaxies to condense. Still others have electromagnetic forces that prevent atoms from forming stable configurations. In this infinite cosmic lottery, every possible universe exists, and conscious observers inevitably find themselves in the vanishingly rare examples where complexity and consciousness can emerge. Others see in this fine-tuning something more profound and mysterious. Perhaps consciousness itself plays a fundamental role in shaping reality, as suggested by certain interpretations of quantum mechanics, where observation affects the nature of reality. Or perhaps there are deeper principles we don't yet understand that make our kind of universe not just possible, but inevitable, hidden symmetries or natural selection mechanisms operating at cosmic scales. The Anthropic Principle forces us to confront a humbling truth about our existence. We are either extraordinarily lucky beneficiaries of cosmic chance, or we're embedded in a reality where consciousness and cosmos are connected in ways that transcend our current understanding. Either we're the product of an almost infinitely improbable cosmic accident, winning a lottery with odds beyond comprehension, or we're part of something much larger and more purposeful than we can currently fathom. Emergent Gravity. What if everything we think we know about one of the universe's most fundamental forces is wrong? What if gravity, the force that keeps your feet on the ground, holds planets in orbit around stars, shapes the large-scale structure of the cosmos, and warps space-time itself, is not fundamental at all, but rather an emergent property arising from something deeper, more subtle, and more information-based than we ever imagined. This is the startling proposition of emergent gravity, a theory that reimagines one of nature's most familiar forces as a consequence of quantum information and thermodynamics. It's an idea that would have seemed like pure science fiction just decades ago, but now stands at the cutting edge of theoretical physics, offering potential solutions to some of the deepest mysteries in cosmology while fundamentally challenging our understanding of reality's basic architecture. The story begins with a profound insight about the nature of information and entropy that emerged from studying black holes, those cosmic monsters whose gravitational pull is so intense that not even light can escape once it crosses the event horizon. In the 1970s, physicist Jacob Bekenstein made a discovery that would revolutionize our understanding of space, time, and information itself. He found that black holes have entropy, a measure of disorder or hidden information, but this entropy was proportional to the area of their event horizon, not their volume. This was deeply puzzling because entropy usually relates to the volume of a system, counting the microscopic arrangements of its constituent parts, like the number of ways molecules can be arranged in a gas. The more volume available, the more ways particles can be arranged, and the higher the entropy. But black holes seem to store information on their two-dimensional surfaces, rather than in their three-dimensional interiors, like cosmic hard drives that encoded data on their boundaries rather than throughout their bulk. This insight led to the Holographic Principle, one of the most remarkable discoveries in modern physics. The principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. When you look at a hologram, you see a three-dimensional image, but all the information creating that image is actually stored in the flat, holographic plate. The holographic principle suggests that our entire three-dimensional reality might work the same way. A projection of information encoded on a distant two-dimensional boundary. Emergent gravity takes this insight and pushes it to its revolutionary conclusion, proposing that gravity itself arises from the tendency of quantum information to become more disordered, to increase entropy. This connection between information and gravity isn't just metaphorical, it's deeply mathematical and precise. When matter concentrates in a region of space, it reduces the entropy of quantum information on the boundary of that region by organizing and constraining the information content. Nature, following the fundamental tendency toward maximum entropy, responds by trying to restore disorder. This restoration process manifests as what we perceive as gravitational attraction. The apparent pull of gravity is actually the universe's attempt to maximize information entropy, reorganizing matter and energy to achieve the most disordered, highest entropy state possible. It's as if the cosmos has a built-in preference for chaos, and gravity is simply one way this preference expresses itself. In this view, Einstein's curved space-time is not fundamental, but emerges from underlying quantum processes, much like temperature emerges from the random motion of molecules. You can't point to a single molecule and say, this one is hot, because temperature is a collective property that only makes sense when considering large numbers of particles. Similarly, you can't point to a fundamental gravitational field in emergent gravity theory. But, collectively, quantum information processes create what we experience as gravitational attractions and space-time curvature. This reframing of gravity has profound implications for understanding cosmic phenomena. Consider the mysterious dark matter that astronomers believe outweighs visible matter by a factor of 5 to 1. Despite decades of searching, no one has detected dark matter particles directly, leading to increasingly exotic proposals for what this invisible substance might be. Emergent gravity offers an elegant alternative. What we interpret as dark matter might not be exotic particles at all, but rather a manifestation of how gravity emerges from quantum information in regions where ordinary matter is sparse. The theory predicts gravitational effects that closely match dark matter observations without requiring any new particles. In galaxy clusters and at the edges of spiral galaxies, where dark matter effects are most pronounced, emergent gravity calculations show that the information-based gravitational effects naturally produce the orbital velocities and gravitational lensing we observe. The missing mass isn't missing. It was never there in the first place. What we've been interpreting as the gravitational effects of invisible matter is actually the signature of gravity's informational nature. Even more remarkably, emergent gravity might explain dark energy, the mysterious force accelerating the expansion of the universe. Current cosmological models require that nearly 70% of the universe consists of dark energy, a substance with the bizarre property of creating repulsive gravity. In emergent gravity theory, this acceleration arises naturally from the quantum information structure of spacetime itself, eliminating the need for exotic energy fields with counterintuitive properties. The accelerated expansion emerges from the way quantum information is organized on cosmic scales. As the universe expands, the information content of space changes, and this change creates apparent repulsive effects that manifest as cosmic acceleration. What we interpret as dark energy is actually a consequence of how information entropy evolves in an expanding universe, making the acceleration a natural feature of emergent gravity rather than evidence for mysterious new physics. This theory suggests that at the deepest level, the universe is made not of particles and forces, but of information and its organization. Matter and energy are secondary phenomena, emerging from the way information arranges itself according to quantum mechanical rules. Gravity emerges as a collective behavior of this information, like the flocking behavior that emerges from simple rules followed by individual birds, or the way traffic patterns emerge from the individual decisions of many drivers. The implications extend beyond cosmology to our understanding of space and time themselves. If gravity emerges from information, then space-time, which is fundamentally shaped by gravitational effects, might also be emergent rather than fundamental. The smooth, continuous space-time of Einstein's relativity could be like the smooth surface of a lake, which appears continuous from a distance but reveals its molecular, discrete nature when examined closely enough. This vision transforms our understanding of reality from a mechanical clockwork of particles pushing and pulling each other through forces, to something more akin to a vast, self-organizing information and processing system. The universe becomes less like a machine and more like a computer, with gravity serving as one of the algorithms by which cosmic information organizes itself into the structures and phenomena we observe. The emergence of gravity from information also suggests deep connections between physics and consciousness, since consciousness appears to be fundamentally about information, processing, and organization. While these connections remain speculative, they hint at possibilities for understanding not just how the universe works, but why conscious observers like ourselves can comprehend and study it at all. Cosmic background radiation. In the depths of space, between the stars and galaxies, permeating every cubic centimeter of the universe, there exists a gentle glow, the oldest light in existence, carrying within its subtle patterns the story of creation itself. This is the cosmic microwave background radiation, the afterglow of the Big Bang, and perhaps the most beautiful evidence we have that our universe had a definite beginning in time and space. Every second of every day, trillions upon trillions of ancient photons wash over you, invisible to your eyes but detectable by sensitive instruments tuned to microwave frequencies. These photons are ancient beyond imagination. They began their journey 13.8 billion years ago, when the universe was only 380,000 years old, a cosmic infant compared to its current age. At that primordial time, the universe had cooled just enough from its initial fiery birth for the first atoms to form, suddenly transforming the cosmos from opaque to transparent. The radiation that had been trapped since the very beginning was finally free to travel, and it has been journeying through space ever since, carrying with it an encrypted message about the universe's earliest moments. To understand the significance of this cosmic background radiation, we must journey back to the universe's infancy. Imagine the cosmos at that ancient epoch, a hot, dense fog of electrons, protons, and photons, all mixed together in a plasma so hot and energetic that atoms could not exist. The universe was opaque to light, like being inside a dense cloud, where photons could travel only tiny distances before being absorbed or scattered by free electrons. Light and matter were coupled together in an intricate dance, with photons constantly interacting with the charged particles that filled space. As the universe expanded, it cooled, much like how a compressed gas cools when allowed to expand. The temperature dropped steadily, and after 380,000 years of expansion and cooling, something remarkable happened. The universe had cooled to about 3,000 Kelvin, still hot enough to melt copper, but cool enough for electrons and protons to combine and form the first hydrogen atoms in a process called recombination. Suddenly, like a cosmic sunrise breaking through eternal fog, the universe became transparent to light. At this moment of cosmic dawn, photons that had been constantly absorbed and re-emitted by free electrons were suddenly free to travel unimpeded through space. The light released at that moment, what we now call the cosmic microwave background, filled the universe uniformly, creating a snapshot of the cosmos at the moment of its transition from opacity to transparency. These photons have been traveling through space ever since, largely undisturbed, carrying information about the state of the universe when it was less than 1% of its current age. The cosmic expansion has stretched these photons over billions of years, shifting their wavelengths from the visible and infrared light they originally were into the microwave portion of the electromagnetic spectrum. It's as if the universe itself acts as a cosmic redshift machine, stretching the wavelengths of ancient light as space expands, transforming what was once a brilliant glow into the subtle microwave radiation we detect today. This background radiation is remarkably uniform across the sky, varying in temperature by only tiny fractions, about 1 part in 100,000. This extraordinary uniformity tells a profound story about the early universe. It reveals that 380,000 years after the Big Bang, matter and energy were distributed almost perfectly evenly throughout space, with only the tiniest variations breaking the cosmic smoothness. Yet, within this remarkable uniformity lie the seeds of everything we see today: galaxies, stars, planets, and ultimately, the complex chemistry that gave rise to life. The tiny variations in the background radiation, hot and cold spots differing by mere millionths of a degree, represent quantum fluctuations from the universe's first moments, amplified by cosmic inflation to astronomical scales. These minute irregularities were the gravitational seeds that would eventually grow over hundreds of millions of years into the cosmic web of galaxy clusters, filaments, and voids that structure our universe today. In a very real sense, the patterns in this ancient light are the blueprints for everything that exists. Every galaxy cluster, every star, every planet can trace its origin back to these primordial fluctuations. The cosmic background radiation also solves a puzzle that had long troubled cosmologists. Different regions of the sky show us light that has traveled from areas of space so distant that they could never have communicated with each other, even at the speed of light in the time available since the Big Bang. Yet these causally disconnected regions show nearly identical temperatures, differing by less than 1 part in 100,000. How could regions that had never been in contact achieve such similar conditions? This mystery helped lead to the theory of cosmic inflation, the idea that in the universe's first fraction of a second, space underwent a period of exponential expansion, growing faster than the speed of light. During this inflationary epoch, quantum fluctuations that started smaller than atomic nuclei were stretched across vast scales, creating the patterns we see in the cosmic background radiation. Regions of space that are now separated by billions of light years were once in close contact, explaining their similar temperatures and properties. The cosmic background radiation provides our most precise cosmic timestamp, allowing scientists to determine the age and composition of the universe with remarkable accuracy. By analyzing its properties in detail, researchers have determined that ordinary matter, the stuff of stars, planets, and living beings, makes up only about 5% of the universe. Dark matter, invisible but gravitationally influential, comprises about 27%, while dark energy, driving the accelerated expansion of space, accounts for the remaining 68%. This ancient light carries other secrets as well, encoded in subtle patterns that require sophisticated analysis to decode. The polarization of the background radiation, the preferred orientation of the light waves, reveals information about the earliest moments of cosmic history, potentially providing evidence for gravitational waves from inflation itself. These would be ripples in space-time from the universe's birth, imprinted on the cosmic background radiation like fossil impressions of creation's first moment. Each photon in the cosmic background radiation is a messenger from the past, carrying information that has remained essentially unchanged for nearly 14 billion years. These particles of light have witnessed the entire history of the universe, traveling through space as galaxies formed, as stars ignited and died, as planets coalesced and life emerged. They carry within their properties a record of cosmic evolution, from the universe's simplest state to its current complexity. The detection and study of cosmic background radiation represents one of humanity's greatest intellectual achievements. When you consider that we can use radio telescopes to detect and analyze light that has been traveling since the universe was in its infancy, it becomes clear that we are truly cosmic archaeologists, digging through layers of space and time to uncover the story of our origins. When you look up at the night sky, you're seeing light from stars and galaxies as they were years, centuries, or millions of years ago. The further you look, the further back in time you see. But the cosmic background radiation lets us see much further back than any star or galaxy, to the very moment when the universe became transparent. It's our cosmic baby picture, capturing the universe in its infancy, and it remains one of the most compelling pieces of evidence that our cosmos had a definite beginning in a hot, dense state we call the Big Bang. This ancient glow connects us directly to the moment of cosmic dawn, making every one of us a part of the universe's ongoing story of evolution and discovery. Quantum foam. Picture the surface of the ocean on a perfectly calm day. From a distance, it appears as smooth as glass, a mirror reflecting the sky with crystalline perfection. But move closer, and you begin to see the gentle undulations of waves. Closer still, and you notice the foam and bubbles dancing on the surface. Now, imagine diving beneath the waves, deeper and deeper, until you reach a realm where the very concept of a smooth surface dissolves into chaos. A place where the ocean itself becomes a tempest of creation and destruction, where droplets of water spontaneously burst into existence and vanish in the same instant. This is the strange reality that quantum foam suggests lies at the foundation of space itself. What we perceive as the empty vacuum of space, that seemingly serene void between stars and planets, may be nothing like the peaceful emptiness it appears to be. Instead, at the smallest conceivable scales, space itself might be boiling with activity, a frothy mixture of virtual particles and fluctuating geometry that challenges our most basic intuitions about the nature of reality. This is quantum foam, a concept that emerges when we push our understanding of quantum mechanics and relativity to their absolute limits. To grasp the scale at which this cosmic turbulence occurs, we must journey to dimensions so small that they make atomic nuclei seem like vast cosmic structures. We're talking about the Planck length, approximately 10 to the power of minus 35 meters, a distance so infinitesimally small that if you were to magnify a proton to the size of the observable universe, the Planck length would still be smaller than a human hair. At this scale, the smooth fabric of space-time that Einstein described begins to break down, replaced by something far more chaotic and dynamic. The mathematics of quantum mechanics tells us that at these tiny scales, the uncertainty principle reigns supreme. Energy and time become locked in a cosmic dance of uncertainty, where the more precisely we try to pin down one, the more the other slips away from our grasp. This fundamental uncertainty creates a strange permission in the laws of physics. It allows the universe to borrow energy from the vacuum, creating pairs of particles that flash into existence and then annihilate each other before the cosmic accountant notices the transaction. These virtual particles are not merely mathematical abstractions. They have real, measurable effects on the world we inhabit. They subtly influence the behavior of atoms, contributing to forces we can detect in our laboratories. The Casimir effect, where two metal plates placed extremely close together experience an attractive force, is a direct consequence of these quantum fluctuations. The vacuum between the plates contains fewer virtual particles than the space outside, creating a pressure difference that pushes the plates together, a ghostly hand reaching out from the quantum foam to touch our macroscopic world. But quantum foam suggests something even more profound than virtual particles popping in and out of existence. It proposes that space and time themselves, the very stage upon which all physics plays out, are not the smooth, continuous backdrop we imagine them to be. Instead, they are granular, choppy, constantly fluctuating at the smallest scales. The geometry of space-time itself writhes and bubbles like a pot of boiling soup, with tiny wormholes and bridges spontaneously forming and dissolving in time frames shorter than the briefest moment we can imagine. This foam-like structure of reality emerges from the marriage of quantum mechanics and general relativity. Einstein's theory tells us that mass and energy curve space-time, creating the phenomenon we experience as gravity. But quantum mechanics adds a crucial twist. If virtual particles are constantly appearing and disappearing, their energy must be constantly curving space-time in random, chaotic ways. The result is not the smooth curvature of Einstein's elegant equations, but a landscape that writhes and fluctuates like a turbulent sea. At these scales, our familiar concepts of distance and duration lose their meaning. What does it mean to travel from point A to point B when the space between them is constantly reshaping itself? How do we measure time when the very fabric in which time is embedded is in constant flux? The quantum foam suggests that beneath the apparent solidity of our experience lies a reality so fundamentally uncertain that existence itself becomes probabilistic rather than deterministic. The implications ripple outward from the microscopic to the cosmic. Some theories suggest that quantum foam might be responsible for the mysterious dark energy that appears to be accelerating the expansion of our universe. Others propose that the Big Bang itself might have emerged from a particularly violent fluctuation in this primordial foam, a bubble that grew and cooled to become everything we see around us. In this view, our entire universe might be just one foam bubble among countless others, each containing its own physics, its own particles, its own story of cosmic evolution. The foam also raises profound questions about the nature of information and memory in the universe. If space-time is constantly fluctuating at the smallest scales, how is information preserved? How do the laws of physics maintain their consistency across such a chaotic foundation? Some physicists suggest that the foam itself might be the medium through which information flows, with the quantum fluctuations encoding and preserving the history of every interaction that has ever occurred. Perhaps most remarkably, quantum foam offers us a glimpse into the ultimate democracy of existence. At the deepest level, every point in space is equal in its turbulence, every moment in time equally uncertain. The grandest galaxy and the smallest particle both rest upon the same foamy foundation, subject to the same fundamental uncertainties. In this view, stability and permanence, the solid ground beneath our feet, the reliable progression of cause and effect, are not fundamental features of reality, but rather statistical emergencies, temporary patterns that arise from the chaos like whirlpools in a stream. The quantum foam reminds us that beneath every appearance of solidity lies an ocean of possibility. The chair you sit in, the air you breathe, the thoughts flowing through your consciousness, all of these seemingly stable phenomena are manifestations of patterns that have emerged from and continue to dance upon this restless creative foundation. We are not separate from this cosmic turbulence, but are expressions of it, temporary arrangements of foam that have learned to contemplate their own existence. In contemplating quantum foam, we confront the deepest mystery of existence, how something as chaotic and uncertain as quantum fluctuations can give rise to a universe of such apparent order and beauty. Perhaps the answer lies in recognizing that chaos and order are not opposites but partners in the cosmic dance, each giving meaning to the other. The foam's restless energy provides the raw material of creation, while the patterns that emerge from it, particles, forces, planets, life, consciousness, represent the universe's endless creativity in finding new ways to organize and express itself. This vision transforms our understanding of emptiness itself. What we call the vacuum is not empty but pregnant with infinite possibility, a creative matrix from which all things emerge and to which they return. In the quantum foam, destruction and creation are not separate processes, but different aspects of the same fundamental rhythm, the cosmic heartbeat that pulses at the very foundation of existence. Supersymmetry. Imagine standing before a mirror that reflects not just your physical form, but reveals a hidden twin, a shadow self that shares your essence yet differs in fundamental ways. This doppelganger moves when you move, exists when you exist, but remains forever invisible to your eyes, detectable only through the subtle influence it exerts on the world around you. This is the breathtaking proposition of supersymmetry, a theory suggesting that every particle we know and love in our universe has a mysterious partner, a mirror twin dwelling in the shadows of reality, waiting to be discovered. In the elegant dance of particles that comprises our cosmos, we've long recognized two distinct families, the fermions and the bosons. Fermions are the building blocks of matter, electrons, quarks, neutrinos, the particles that make up the substance of everything we touch and see. They are like the introverted members of nature's party, following the Pauli exclusion principle, which ensures that no two identical fermions can occupy the same quantum state simultaneously. Bosons, on the other hand, are the social butterflies of the particle world. Photons, W and Z bosons, gluons, the force carriers that mediate all interactions between particles, happily crowding together in the same quantum state. For decades, these two families seemed as different as night and day, playing entirely separate roles in the cosmic drama. But supersymmetry whispers of a deeper unity, suggesting that this apparent division is merely a surface illusion. According to this elegant theory, every fermion has a bosonic partner, and every boson has a fermionic twin. The electron, that fundamental building block of atoms, is paired with a particle called the selectron. The photon, the massless particle of light, has a partner known as the photino. Each quark is matched with a corresponding squark, each neutrino with a sneutrino. The names themselves hint at the profound symmetry at play, thus prefix denoting the supersymmetric partners, creating a lexicon that sounds like poetry written in the language of theoretical physics. These shadow particles don't just share names with their visible counterparts, they share quantum numbers, charges, and fundamental properties. Yet they differ in one crucial aspect, their spin, the intrinsic angular momentum that defines whether a particle behaves as matter or as a force carrier. This symmetry suggests something almost mystical about the architecture of reality. If supersymmetry is correct, then for every particle dancing in the light of our awareness, there exists an equal and opposite partner dancing in the darkness beyond our current perception. It's as if the universe maintains a perfect balance, a cosmic yin and yang where every manifestation of matter is matched by a hidden manifestation of force, and every force carrier is balanced by an unseen piece of matter. The mathematical beauty of supersymmetry extends far beyond mere particle pairing. It offers solutions to some of the most vexing problems in modern physics, like a master key that unlocks multiple doors simultaneously. One of the greatest mysteries of our time is the hierarchy problem, why gravity is so much weaker than the other fundamental forces. In our everyday experience, electromagnetic forces easily overcome gravity when a simple magnet lifts a paperclip against the pull of the entire Earth. Supersymmetry suggests that the quantum fluctuations contributed by particles and their superpartners naturally cancel each other out, preventing certain calculations from spiraling toward infinity and maintaining the delicate balance of forces we observe. Perhaps even more tantalizing is supersymmetry's potential connection to dark matter, that invisible substance that comprises roughly 5 times more of the universe than all the ordinary matter we can see. The lightest supersymmetric particle, often called the neutralino, emerges from the theory as a perfect dark matter candidate. It would be stable, electrically neutral, and interact only weakly with ordinary matter, precisely the properties needed to explain the gravitational effects we observe on galactic scales, while remaining invisible to our telescopes. In the supersymmetric vision of reality, our visible universe represents only half of the cosmic story. The other half exists in a realm of heavy, unstable particles that decay so quickly they leave barely a trace of their existence. These superpartners are like quantum ghosts, manifesting only in the briefest of moments before dissolving back into the vacuum from which they emerged. Their masses are likely hundreds or thousands of times greater than their familiar counterparts, which explains why we haven't observed them directly in our particle accelerators. The theory transforms our understanding of the early universe as well. In the first moments after the Big Bang, when temperatures were unimaginably high and energy densities beyond our comprehension, supersymmetry may have been unbroken. Particles and their superpartners would have been indistinguishable, dancing together in perfect harmony. Only as the universe cooled and expanded did this pristine symmetry shatter, leaving us with the asymmetric reality we inhabit today, where ordinary particles remain light and stable, while their superpartners became heavy and ephemeral. This breaking of supersymmetry is not a failure of the theory, but rather its most profound insight. Just as a perfectly spherical droplet of water naturally breaks into irregular shapes as it falls, the perfect symmetry of the early universe naturally evolved into the rich complexity we observe today. The mechanism by which this symmetry breaking occurred may hold the key to understanding why our universe has the particular mix of particles and forces that allows stars to shine, planets to form, and life to emerge. The search for supersymmetric particles has become one of the great quests of modern physics, driving the construction of ever more powerful particle accelerators and sensitive detectors. Each collision in the Large Hadron Collider represents a moment when we briefly recreate the conditions that existed shortly after the Big Bang, hoping to catch a glimpse of these elusive superpartners. Every null result teaches us something new about the energy scales at which supersymmetry might reveal itself, pushing the theory into new and more exotic territories. Yet the continued absence of direct evidence for supersymmetric particles has led to deeper questions about the nature of this hidden mirror. Perhaps the superpartners are even heavier than we initially expected, lurking at energy scales just beyond our current reach. Or perhaps supersymmetry manifests in ways more subtle than we imagined, revealing itself not through the dramatic production of new particles, but through tiny deviations in the behavior of particles we already know. The implications of supersymmetry extend beyond particle physics into the realm of cosmology and even consciousness itself. If every aspect of the material world has an invisible partner, what does this say about the nature of existence itself? Are there supersymmetric analogs to biological processes, to thoughts, to the very phenomenon of awareness? The theory suggests that reality operates on multiple levels simultaneously, with visible and invisible aspects that are forever linked yet forever separate. In contemplating supersymmetry, we confront the possibility that everything we consider real and substantial represents only half of a greater whole. The atoms that make up our bodies, the light that illuminates our world, the forces that bind matter together. All of these familiar phenomena may be merely the visible peaks of a vast mountain range, whose invisible foothills extend far beyond our current perception. This vision of reality as fundamentally dual in nature resonates with ancient philosophical traditions, while pointing toward a future where the boundaries between the seen and unseen, the known and unknown, may finally be bridged. Supersymmetry reminds us that the universe may be far richer and more mysterious than even our wildest scientific imagination has dared to propose, holding within its quantum depths reflections and shadows that await our discovery. Grand unified theories. In the beginning, there was unity, not the unity of religious creation myths or philosophical abstractions, but something far more profound, a state where all the fundamental forces that now govern our universe were indistinguishable from one another, woven together in perfect harmony, like colors blended into pure white light. This is the breathtaking vision offered by grand unified theories, perhaps the most ambitious attempt in human history to understand the deepest architecture of reality by revealing the hidden connections that bind all natural forces into a single, elegant tapestry. Today we live in a universe of apparent division. 4 fundamental forces rule the cosmos. Gravity holds planets in their orbits. Electromagnetism powers our technology and binds electrons to nuclei. The strong nuclear force welds protons and neutrons together, and the weak nuclear force governs radioactive decay and stellar fusion. These forces appear as different as earth, air, fire, and water, distinct elements with their own characteristics and domains. Yet beneath this surface diversity, physicists have long suspected a deeper unity. The first hint came when Maxwell revealed that electricity and magnetism were actually two faces of the same underlying force. His equations showed that changing electric fields create magnetic fields and vice versa, in an eternal dance that manifests as electromagnetic radiation. Suddenly, the light from distant stars and the spark from amber revealed themselves as expressions of the same fundamental principle. This triumph planted a seed. If electromagnetism could emerge from unifying two forces, perhaps all forces spring from a single source. Grand unified theories seek to demonstrate that the strong, weak, and electromagnetic forces are merely different aspects of one grand unified force. The mathematical architecture of these theories is breathtaking in their scope and ambition. They propose that at incredibly high energies, temperatures from the first fraction of a second after the Big Bang, the distinctions between forces dissolve completely. At these cosmic furnace temperatures, particles would possess such enormous energies that the boundaries between different interactions would simply melt away. A proton could transform into an electron, and the rigid categories that define our world would reveal themselves as shadows cast by a higher dimensional unity. This unification occurs through a process that mirrors the way a perfect sphere breaks into complex shapes as it cools and crystallizes. In the primordial universe, when temperatures were unimaginably high, there existed perfect symmetry. All forces were one, all particles interchangeable. But as the universe expanded and cooled, this pristine symmetry began to break spontaneously, like a pencil balanced on its point that must eventually fall in some particular direction. The single primordial force fractured into the four forces we observe today, each carrying within it the memory of its unified origin. The elegance of grand unified theories lies in their specific predictions. They suggest that protons, those seemingly eternal building blocks, are not actually stable forever. Given enough time, perhaps 10 to the power of 34 years or more, even protons should decay. This transforms our understanding of matter itself, suggesting that all atoms are merely temporary arrangements in a cosmic recycling process operating on unimaginable timescales. The theory also predicts magnetic monopoles, isolated magnetic poles carrying only a single type of charge. Their discovery would provide compelling evidence for grand unification. The elegance of grand unified theories lies not just in their conceptual beauty, but in their specific predictions. They suggest that protons, those seemingly eternal building blocks of atomic nuclei, are not actually stable forever. Given enough time, perhaps 10 to the power of 34 years or more, even protons should decay, dissolving back into the more fundamental particles from which they emerged. This prediction transforms our understanding of matter itself, suggesting that all the atoms in our bodies, all the elements in the periodic table, are merely temporary arrangements in a cosmic recycling process that operates on timescales almost beyond human comprehension. The theory also predicts the existence of exotic particles called magnetic monopoles, isolated magnetic poles that would be the magnetic equivalent of electric charges. Unlike ordinary magnets, which always have both north and south poles, these theoretical objects would carry only a single type of magnetic charge. Their discovery would provide compelling evidence for grand unification as they emerge naturally from the mathematical structure of these theories, like inevitable consequences of deep symmetry. Perhaps most remarkably, grand unified theories offer an elegant explanation for one of the most fundamental asymmetries in our universe: why matter exists at all. In the perfectly symmetric early universe, matter and antimatter should have been created in equal quantities. When they met, they should have annihilated each other completely, leaving behind only pure energy. Yet, here we are, living in a universe made almost entirely of matter, with antimatter appearing only in rare cosmic ray interactions and laboratory experiments. Grand unification suggests that, in the earliest moments of cosmic history, tiny asymmetries were introduced during symmetry breaking, subtle preferences that favored matter over antimatter by just 1 part in a billion. This minuscule imbalance resulted in the matter-dominated universe we inhabit today. Our very existence may be a consequence of broken symmetry, The theories also predict stable, weakly interacting particles that could account for dark matter, relics from the symmetry-breaking epoch that have persisted throughout cosmic history. Yet, for all their mathematical beauty and conceptual elegance, grand unified theories remain tantalizingly beyond direct experimental verification. The energies required to directly test grand unification are roughly 1 trillion times greater than what our most powerful particle accelerators can achieve. It's as if we're trying to understand the architecture of a vast cathedral by examining individual grains of sand with a magnifying glass. The full structure remains hidden, revealed only through indirect evidence and mathematical inference. This has led physicists to become cosmic archaeologists, searching for fossil evidence in the cosmic microwave background, monitoring underground detectors for proton decay, and scanning skies for surviving magnetic monopoles. The quest for grand unification has also driven the development of increasingly sophisticated mathematical tools. Group theory, topology, and advanced symmetry principles have become the languages in which physicists explore the deepest structures of reality. These mathematical frameworks reveal hidden connections and patterns that would be invisible to more conventional approaches, suggesting that the universe's architecture may be far more elegant and interconnected than our everyday experience suggests. In pursuing grand unified theories, we confront profound questions about the nature of knowledge itself. If these theories are correct, then the diversity and complexity we observe around us, the rich tapestry of particles and forces that make up our world, may be nothing more than a low-energy approximation of a far simpler and more beautiful underlying reality. We would be like inhabitants of a shadow world, seeing only projections of higher dimensional truths that exist beyond our direct perception. Grand unified theories remind us that the universe may be far more elegant and unified than our fragmented experience suggests. They point toward a reality where the boundaries between different types of phenomena are artificial constructs of our limited perspective, where all the richness and complexity of existence emerges from variations on a single, beautiful theme. In seeking this ultimate unity, we are not just pursuing abstract knowledge, but following a deep human intuition that beneath the surface chaos of experience lies an underlying order waiting to be discovered and celebrated. The Baryon asymmetry problem. You exist, and that is the greatest mystery in the universe, not in some philosophical or spiritual sense, but as a fundamental violation of what physics tells us should have happened in the earliest moments of cosmic history. Every atom in your body, every star in the sky, every grain of sand on every beach, all of it represents a cosmic crime scene, evidence of the most profound asymmetry in nature. This is the Baryon asymmetry problem, the deepest puzzle about why there is something rather than nothing, and why we are here to ponder the question at all. In the beginning, there should have been perfect balance. According to our best understanding of particle physics, the Big Bang should have created matter and antimatter in precisely equal quantities, a cosmic yin and yang, where every electron was matched by a positron, every proton by an antiproton, every particle by its perfect mirror opposite. These complementary pairs should have annihilated each other in brilliant flashes of pure energy, leaving behind a universe filled with nothing but photons racing through empty space for eternity. Yet, here we are, living proof that this cosmic symmetry was somehow broken. We inhabit a universe made almost entirely of matter, where antimatter appears only as exotic curiosities in cosmic ray showers and laboratory experiments. The very fact that you can read these words, that planets orbit stars, that chemistry creates complexity, all of this depends upon a tiny but crucial imbalance that emerged from the primordial fire of creation. The scale of this mystery becomes clear when we consider the numbers. For every billion particle-antiparticle pairs that annihilated each other in the early universe, exactly one extra particle of matter survived. This ratio, 1 part in a billion, represents the entire material legacy of the Big Bang. Everything we see around us, from the smallest bacterium to the largest galaxy cluster, emerged from this minuscule surplus, this cosmic rounding error that somehow became the foundation of all existence. This revelation transforms our understanding of rarity and abundance. What we perceive as a universe teeming with matter is actually the aftermath of an almost perfect annihilation. The earth beneath your feet, the air you breathe, your own body. All of it represents the remnants of a cosmic holocaust so complete that it left behind only the faintest trace of its original material. We are not living in a matter-rich universe. We are living in the ghost of a universe that once contained both matter and antimatter in equal measure. The mystery deepens when we consider that this asymmetry appears to violate some of the most fundamental symmetries in physics. According to the standard model of particle physics, the laws of nature should treat matter and antimatter with perfect equality. Every process that creates a particle should be matched by a corresponding process that creates its antiparticle. Every force that acts on matter should act with equal strength on antimatter. The universe should be perfectly ambidextrous, showing no preference for matter over its antimatter twin. Yet, something in the early universe broke this pristine symmetry, introducing a subtle bias that favored matter over antimatter. This violation is so fundamental that it challenges our deepest assumptions about the nature of physical law. It suggests that somewhere in the cosmic code, hidden within the mathematics that govern reality itself, there exists a preference, a cosmic handedness that tilts the scales of existence toward matter rather than void. The search for this hidden asymmetry has led physicists to explore some of the most exotic corners of theoretical physics. One possibility lies in the behavior of certain particles that seem to violate what physicists call CP symmetry, the combined symmetry of charge conjugation and parity. These violations are incredibly subtle, occurring in less than 1% of certain particle decays, yet they represent cracks in the perfect mirror of matter-antimatter symmetry. The most dramatic of these violations occurs in the behavior of kaons and B-mesons, particles that contain strange and bottom quarks. These particles exhibit a slight preference for decaying into matter rather than antimatter, creating a tiny imbalance that ripples through the quantum foam. While these violations are far too small to account for the cosmic matter surplus directly, they provide proof of principle that nature does indeed break the sacred symmetry between matter and antimatter. Another avenue of investigation focuses on the role of neutrinos, those ghostly particles that barely interact with ordinary matter, yet outnumber atoms by more than 1 billion to 1. Recent discoveries have revealed that neutrinos possess mass and can oscillate between different types as they travel through space. This behavior suggests that neutrinos might violate CP symmetry in ways that could have amplified the tiny matter-antimatter imbalance in the early universe. The mystery also involves the concept of baryogenesis, the process by which the cosmic matter surplus was generated. For this process to work, 3 specific conditions must have been met in the early universe. First, there must have been reactions that could change the number of baryons, particles like protons and neutrons that make up atomic nuclei. Second, both charge conjugation and CP symmetry must have been violated. Third, these processes must have occurred out of thermal equilibrium, preventing the universe from erasing any imbalance as quickly as it was created. These conditions, first articulated by physicist Andrei Sakharov, provide a roadmap for understanding how cosmic asymmetry could have emerged. Yet, identifying the specific mechanisms that satisfy these conditions remains one of the greatest challenges in modern physics. The processes responsible for our existence may have occurred at energy scales far beyond our ability to recreate in laboratories. During the first tiny fraction of a second after the Big Bang, when the universe was hotter and denser than anything we can directly observe. Some theories propose that the asymmetry emerged during phase transitions in the early universe, moments when the fundamental forces underwent dramatic changes as the cosmos cooled and expanded. During these transitions, the perfect symmetries that governed the primordial universe may have broken spontaneously, like a pencil balanced on its point that must eventually fall in one direction or another. The direction of this cosmic fall determined whether we would live in a universe of matter or antimatter. Other theories suggest that the asymmetry has even more exotic origins, perhaps arising from the decay of super-heavy particles that existed only in the first moments after the Big Bang, or from interactions involving extra dimensions of space that remain hidden from our direct observation. Some proposals even invoke violations of time reversal symmetry, suggesting that the arrow of time itself played a role in determining the cosmic preference for matter over antimatter. The implications of Baryon asymmetry extend far beyond particle physics into questions of cosmic purpose and meaning. If the matter-antimatter balance had been perfect, if that crucial one part in a billion excess had never existed, the universe would have evolved into a dark, empty expanse populated only by photons and perhaps a few light particles. There would be no atoms, no chemistry, no stars, no planets, no life, no consciousness to contemplate existence. In this sense, the Baryon asymmetry problem reveals that our existence hangs by the thinnest of threads. We are here not because the universe was designed to produce matter, but because of a tiny, possibly random fluctuation in the cosmic balance sheet. This realization is simultaneously humbling and awe-inspiring. Humbling because it reveals how precarious our existence truly is, and awe-inspiring because it demonstrates that even the smallest departures from perfect symmetry can have consequences beyond imagination. The problem also raises profound questions about the nature of uniqueness in the universe. Was the specific value of the matter-antimatter asymmetry inevitable, determined by deeper physical principles we have yet to discover? Or was it essentially random, one possible outcome among many in a cosmic lottery that we happen to win? If other universes exist with different values of this asymmetry, most would be sterile and empty, while a precious few might harbor the complexity necessary for stars, planets, and life. As we continue to probe this mystery through increasingly sophisticated experiments and observations, we are essentially investigating the conditions of our own existence. Every measurement of CP violation, every study of neutrino oscillations, every simulation of the early universe brings us closer to understanding why we are here at all. The Baryon asymmetry problem reminds us that existence itself is not a given, but a phenomenon that requires explanation. A cosmic accident so improbable and so crucial that it transforms the very meaning of what it means to be. Cyclic universe models. Time is not a river flowing toward an ocean, but a vast wheel turning through eternity. This is the profound vision offered by cyclic universe models, theories that challenge our most basic assumptions about cosmic history by suggesting that our universe is not a single story with a beginning and an end, but rather one chapter in an infinite book, a cosmos that breathes in and out across eons, expanding and contracting in an eternal rhythm that has no first beat and will have no final silence. The conventional narrative tells us our universe began in the Big Bang, roughly 14 billion years ago, expanding ever since as galaxies race away from each other into an increasingly dark future. We inhabit a universe with a definite biography, a story that began with a bang and will end in heat death or gravitational collapse. But cyclic models whisper a different story entirely. They suggest that what we call the Big Bang was not the beginning of everything, but merely the most recent in an infinite series of cosmic renewals. Our expanding universe, in this view, is like the inhalation phase of some vast cosmic breathing, destined to eventually exhale in a period of contraction that will compress all of space back toward a singular point, only to bounce back in another Big Bang, starting the cycle anew. This vision transforms our understanding of cosmic time from linear to circular. Instead of living in a universe with a unique history, stretching from initial creation to final destiny, we would inhabit a cosmos that has already lived through countless previous lives, each one lasting billions of years, each one containing its own galaxies, stars, planets, and perhaps even its own forms of life and consciousness. The atoms in your body, the light from distant stars, the very fabric of space-time itself, all of it would be recycled material from previous cosmic cycles, ancient beyond our ability to comprehend. The mathematical foundation for these models emerges from modifications to Einstein's general relativity that allow the universe to avoid the crushing singularities that seem to mark both the beginning and potential end of cosmic history. In standard cosmology, the Big Bang represents a point where the laws of physics break down, where density and temperature become infinite, and the very concept of time loses its meaning. But cyclic models propose that quantum effects, or exotic forms of matter, might prevent this collapse, causing the universe to bounce at the moment of maximum compression, transforming contraction into expansion in a seamless transition. One of the most elegant versions involves the ekpyrotic scenario, where our universe exists as a membrane in higher dimensional space, occasionally colliding with another membrane in the cosmic crashes that create Big Bangs. These collisions occur with regularity across vast periods, each one erasing the previous cycle and initiating new expansion. The beauty of cyclic models lies in their ability to solve some of the most perplexing problems in conventional cosmology. The flatness problem, why space appears to be geometrically flat when it could have any curvature, becomes irrelevant if the universe has had infinite time to smooth out its geometry through countless cycles. The horizon problem, why distant regions of the universe have the same temperature despite never being in causal contact, dissolves if they were once connected in a previous cycle when the universe was smaller. Perhaps most remarkably, cyclic models explain the mysterious dark energy accelerating our expansion. In these theories, dark energy oscillates between positive and negative values over cosmic time, pushing galaxies apart during expansion, becoming attractive during contraction to help compress the universe toward its bouncing point. The implications for the arrow of time are particularly profound. In a cyclic universe, the second law of thermodynamics, which states that entropy always increases, would need to be reconsidered. Perhaps entropy is reset with each cycle, allowing the universe to begin each new phase with maximum order and minimum chaos. Or perhaps entropy continues to accumulate across cycles, with each new universe slightly more disordered than the last, creating a kind of cosmic evolution that plays out over temporal scales almost beyond imagination. This raises questions about memory across cosmic cycles. If our universe has lived through countless iterations, what traces might remain from ancient epochs? Could information survive the compression of a big crunch and explosion of a subsequent Big Bang? Some theories suggest certain features of space-time might persist across cycles, carrying forward a genetic code that influences each new universe's structure. The cyclic perspective also transforms our understanding of cosmic destiny. Instead of facing inevitable heat death or catastrophic collapse, we would be living in a universe that is essentially immortal, capable of renewing itself indefinitely. Each cycle might last hundreds of billions of years, giving ample time for the full flowering of cosmic complexity, the birth and death of countless generations of stars, the formation and dissolution of galaxies, the emergence and extinction of countless forms of life across countless worlds. Yet, this immortality comes with a strange form of cosmic amnesia. If the cycles are truly periodic, then everything that has ever happened will happen again. And everything that ever will happen has already occurred in previous cycles. The thoughts you are thinking now, the words on this page, the entire history of human civilization, all of it would be destined to repeat with perfect precision in future cycles, just as it has repeated in past ones. This raises the specter of eternal recurrence, the idea that existence is not just cyclical, but precisely repetitive. Every choice you make, every moment of joy or sorrow, every triumph and tragedy in human history would be fated to replay across infinite cycles of cosmic time. You have lived this exact life countless times before, and will live it countless times again, each time with no memory of the previous iterations, each time experiencing it as if for the first time. Some cyclic models avoid this disturbing implication by incorporating randomness that would ensure each cycle differs from its predecessors. Small quantum fluctuations during the bounce might seed each universe with unique density patterns, leading to different arrangements of matter. The cycles would be similar but not identical, like variations on a cosmic theme, exploring every possible arrangement across infinite time. The observational evidence for cyclic models remains tantalizingly indirect. Unlike the Big Bang theory, which makes specific predictions about the cosmic microwave background radiation and the abundance of light elements, cyclic models are harder to test directly. The extreme conditions during the bounce phase would likely erase most evidence of previous cycles, leaving behind only the faintest traces that might be detectable with incredibly sensitive instruments. However, recent observations have provided intriguing hints. Certain anomalies in the cosmic microwave background might be echoes from previous cycles. The discovery that our universe's expansion is accelerating has also breathed new life into cyclic models that can naturally account for this mysterious acceleration. In contemplating cyclic universe models, we confront perhaps the deepest question about the nature of existence, whether the cosmos is a story with a beginning and an end, or an eternal performance that has no opening act and no final curtain. These theories suggest that we might be living not in a universe but in a multiverse of time, a reality where past, present, and future become meaningless categories, where everything that can happen does happen, not just somewhere else in space, but someone else in time. The cyclic vision offers both comfort and vertigo. Comfort in the knowledge that the universe is not racing toward inevitable death, but possesses a form of immortality that transcends any individual cycle. Vertigo at the realization that our entire cosmic history, from the first stirrings of matter in the primordial plasma to the final thoughts of the last conscious beings, might be just one breath in an infinite cosmic respiration that has been occurring for eternity and will continue long after our particular cycle has faded into memory. In this eternal dance of expansion and contraction, we find ourselves not as witnesses to a unique cosmic drama, but as temporary patterns in an infinite kaleidoscope, brief arrangements of matter and energy that emerge, evolve, and dissolve in the endless turning of the cosmic wheel. I hope you enjoyed this video and it could transport you into the wonderful mysteries of our universe. If you haven't fallen asleep yet, you'll find another interesting video about our universe on the screen. Sleep well and dream of the secrets of the cosmos.